Good morning. Welcome to the fourth week of AGCE 515 class. Today we will finish about the characteristics or the properties of a clay liner. So the topic that we will be dealing with today first we'll talk about the factors that affect hydraulic conductivity. Last week we talked about what is hydraulic conductivity and how do we measure them and what is the requirement for liners. Today we'll check what are the factors that control the hydraulic conductivity. We'll also talk about the measurement of hydraulic conductivity in lab and in field, and in the third half we'll talk about the compaction characteristics. Third quarter we'll talk about the compaction characteristics. So let's begin first the factors that affect the hydraulic conductivity. You see, mostly the soil is called well graded if they have different size particle in the soil. We measure that based on the coefficient of uniformity and coefficient of curvature that we dealt with before. So the hydraulic conductivity is less if we have more fine-grained particle in it, and it is obviously is obvious because if we have coarse-grained particle, the voids created by those coarse-grained particles are pretty big. And if we have fine-grained soil, the fine-grained soil will go inside those voids to increase density and reduce the pore space, and that would reduce the hydraulic conductivity. Okay, so this is one example you can see here. The hydraulic conductivity that we need is 10 to the power negative 7 centimeter per second that we repeatedly talked about, and these are the data that they got. And you see what you can see, the trend is higher the percentage of fine, that is percentage of silt and clay, that is percentage of the soil finer than number 200 sieve or 75 micrometer. So higher the percentage, lower the hydraulic conductivity. You could clearly see that, right? If the hydraulic conductivity is, if the percentage of fine is more than 95%, it was getting almost constant. But with the increase in percentage of fine, hydraulic conductivity decreases. Even you could see almost twofold decrease. Okay, so as I mentioned before, well-graded soil has definitely higher, lower hydraulic conductivity if the other parameters are same. But there, when we add fines, then that will reduce if we add fines, that will reduce the hydraulic conductivity by several orders. For example, here you can see by changing the percentage of fine from 50% to 95%, let's say, or 90%, it reduced the hydraulic conductivity by 2 log cycle, almost 2 log cycle. Okay, so the reason I brought this topic in is sometimes what happens is we have soil in the field that you don't want to give up, you don't want to throw it away, right there. But if you add, and if you separate the soils, and if you add enough fine in the soil, okay, you separate the soil based on the gradation or the particle size, and then recalculate the amount of fine required to make 20% fine, 50%, 60%, 70% fine, depending on what we need, and then add that fine, that is sand plus silt in it, clay plus silt in it, then that will help to reduce the hydraulic conductivity. And we'll continue it. And if now let's go to clay. Okay, so we talked about fine. So if we talk about clay, more the percentage of clay is less than 2 micrometer. You see, within fine, within the soil passing through number 75 micrometer sieve or 200 sieve, there are two different types of soil you have there. One is silt, the other is clay. And silt and clay are classified or separated based on their plasticity characteristics or based on their size. So anything finer than 2 micrometer according to USCS classification system are clays. So if you saw 50, 60, 70, 80% when you talked about fine, but if you increase the percentage of clay in the soil sample, the hydraulic conductivity decreases significantly, right? That you saw reducing the percentage of clay from 15% all the way down to, let's say, 60%, right? So that could reduce the hydraulic conductivity by twofold of log scale, twofold of magnitude in log scale, right? So then most of the time we talk about it when time comes. Most of the time what happens is, if the soil that we are getting in the field is not qualified for compacted clay liner, because yeah, we have enough sand in it, but we don't have enough clay in it, and that causes the hydraulic conductivity that gives you a significantly high hydraulic conductivity value. So there what we do is we purchase a commercially sold clay, highly expensive clay. We talked about monzonite, okay, before, when we talked about clay mineral. So bentonite is a type of commercially available soil that we can buy in market, relative cheap price, but that has significant high percentage of monzonite. So sometimes it is over 90%. The one I saw, I have sodium bentonite I have in the lab, not the monzonite, sodium bentonite I have in the lab, still that has more than 90% monzonite in it. So it is, the bentonite is a soil, highly expansive soil. It has significant amount of monzonite. Okay, so now you see the trend here. So for silt and clay, that is fine. We're talking about 50% to 90%. Now, for clay to get the same reduction in hydraulic conductivity from 10 to the power negative 7 to 10 to the power negative 9, we got less than 60% clay in it, right? But for our purpose, okay, 10 to the power, less than 10 to the power negative 7 centimeter per second. If you're going with the lower bound, you need about 15% clay in it, right? Upper bound, you need about 45% clay. The difference between lower bound and upper bound is, even though you have clay, if the clay has monzonite as the clay mineral, so even for the same percentage of clay fraction, you are getting a lower hydraulic conductivity compared to kaolinite as a clay mineral. So behavior of kaolinite is like silt. Behavior of monzonite is like clay. Okay, and for that reason, if you go back to bentonite thing, so if you add simply to reduce the hydraulic conductivity of the soil from 10 to the power negative 4 to 10 to the power negative 7, right? So we simply need about 5% bentonite in it. So that'll change the reduce the hydraulic conductivity significantly, because bentonite expands when it gets into water, because it has highly expansive clay mineral that we talked, 2-in-1 structure that we talked last week. Okay, so the implication of those minerals in clay fraction is, higher the percentage of monzonite we have, then higher the liquid limit. So higher the liquid limit, it is more plastic the soil is. Okay, and more plastic, less hydraulic conductivity. At the same time, you see, provided the other compaction characteristics are same, and at the same time, the hydraulic, the type of clay and silt is decided based on whether they are plotted above the line or below the line that we dealt with before. Okay, so the hydraulic conductivity if decreases with the increase in liquid limit, obviously, because the liquid limit increases with an increase in expansive clay mineral, or with an increase in percentage of clay. Okay, if you see the lower bound here, you see hydraulic conductivity can be less than 10 to the power negative 7 when the liquid limit is about 15 or 20 for the lower bound, right? For higher bound soil, that this is typically silty, like kaolinitic mineral. This is like the bentonite, monzonitic mineral. So to get same hydraulic conductivity 10 to the power negative 7 per centimeter, you have about 50 liquid limit value of about 50. Okay, so depending on what type of soil we are having. Okay, so that could be silt, that should be clay. Mostly liquid limit and plasticity index is measured for the fines, so the mixture of clay and silt. Okay, so what you can see is, even though you see the hydraulic conductivity, the range for the hydraulic conductivity of -7, the range is significantly big, right? So 15% to almost 50%. But if the liquid, let's say for you have montmorillonitic soil, smectitic soil, hydraulic conductivity increases by almost a twofold in log cycle from when the liquid limit increases from 15 to almost 60 or so. Okay, so this is extremely important. So liquid limit and plasticity index control the hydraulic conductivity of soil. So if you talk about plasticity index, which is liquid limit and minus plastic limit, so combination of liquid limit and plasticity index will tell you whether it is clay or silt. Okay, so if the plastic for the clay soil, you see the hydraulic conductivity decreases significantly when the plastic limit changes from, let's say, 5% to 55 or 60%. Okay, even upper bound, even though hydraulic conductivity, the first silty type of soil, the hydraulic conductivity is 10 to the power -7 that we desire at the plasticity index close to 35, right? And then below that, the hydraulic conductivity decreases with an increase in the plasticity index. So you see, when we decide, when the code, when the manual decides what will be the required plasticity index of that soil, then yes, we need to call it clay. So mostly the requirement is CL or CH or sometimes SC, that is clay sand, is also sometimes qualified for the clay liner, if it gives you required hydraulic conductivity. So the important fact for us is to get required hydraulic conductivity. So if you see the example here, you see the hydraulic conductivity can be achieved at the plasticity index ranging from 5 to 32 or 33, right? So that is the range. But this is one statistical data that someone published, but there are tons of data that we need to go through to make the guideline. Okay, for that reason, always when you see the guideline, you will see, okay, so a guideline is always conservative, and you will see what will be the required plasticity index. For example, if I simply say that the required plasticity index of the soil is, let's say 10%, yeah, if it is smectitic soil, it will give me a required hydraulic conductivity that is lower than 10 to the power 10 to -7 centimeter per second. Right? But if the soil is dominated by the kaolinitic or silty particles, then it will not. For that, 10% does not give me enough hydraulic conductivity. That is 10 to -7 centimeter per second. Okay, that is the logic behind the requirement that we fix for the plasticity index, plastic limit, or the type of soil for compacted clay liner. Okay, mostly, as I'm repeating again, mostly we're more focused on required hydraulic conductivity of 10 to the power -7 because we are concerned about the movement of leachate than anything else. Okay, we need clay because clay has lower hydraulic conductivity that reduce the movement of leachate. Okay, so if we talk about plasticity index, you see, mostly if the plasticity index is more than 7 to 10%, typically we can get the low hydraulic conductivity, as I showed you before. It also depends on the type of clay you have. It also depends on the percentage of clay you have. It is also important because whether it is clay dominated or silt dominated. Okay, that will define two ranges. And for the thing is to achieve 7 to 10%. This is extremely important. Okay, to achieve 7 to 10% hydraulic to achieve 10 to the power -7 hydraulic conductivity of 10 to the power -7 10 to -7 centimeter per second, we may add 7 to 10% soil with 7 to 10% plasticity index, or even more than, let's say, you could see that 35%, 40% plasticity index. Mostly plasticity index is an index, so I mean you may forget about percentage. So let's say 35-40 plasticity index will give you hydraulic conductivity much lower than we need. But the range started from 7 to 10%. So if you go with the lower bound in the previous figure, right, then 7 to 10% plasticity index could provide enough, low enough hydraulic conductivity, right? But you see, as lower you go, always better and safer. If some soil sample gives me hydraulic conductivity less than 10 to negative 9 centimeter per second, it's even better. So we even prefer. The problem with that is if you have highly plastic soil, then when we compact them in the field, then because they are highly plastic, you don't have fully saturated condition, because we control the moisture content also when we compact. So if the soil is highly plastic, then the possibility is the amount of water we are adding in there, will create clot of particles. So there may be segregation or some clots of particle with a lot of water, the other particle remains dry, and when we compact them, the compaction effort may not be uniform. So the one clot we have, or the amount of soil we are compacting, may have enough hydraulic conductivity, required hydraulic conductivity. But the other one that is not clotted, that has less amount of water in it, may still give you much higher hydraulic conductivity than the one that has enough water. For that reason, it is important for us to limit the plasticity index also. That way we are trying to reduce the clot formation during compaction or heterogeneity in the hydraulic conductivity in the compacted soil specimen itself. For that reason, we don't want to go much higher plasticity index. Although that is in the lab situation, that may be desirable to get us much lower hydraulic conductivity. Keep this in mind. This is extremely important. That will limit the upper limit of plasticity index on the soil to be used as the compacted clay liner. There are ways how to deal with that. If you increase the compaction inertia, if we have enough money to increase the compaction inertia, compaction effort, that will break the clots, and that will still give you more or less homogeneous hydraulic conductivity, but that is not cost effective. Okay, so always the good soil liners can be built from soils with very high plasticity index, although the construction is more difficult if we use more inertia in it to break the clots. Okay, and it's always the main reason for that is you see, although and then the other issue with this high plasticity, or the soil with that has high plasticity index or a liquid limit, the other disadvantage is high shrinking and soiling that may cause desiccation, cracking. That we'll talk about that in this class, in this lecture at some point today. But even though it increases shrinking and soiling, because it can absorb more water when it is wet, it can release the same amount of water when it is dry, right? That will increase shrinking and soiling behavior in the soil. At the same time, it is hard to compact uniformly to maintain the homogeneous hydraulic conductivity. Still, the high plasticity soil are desirable, because that will give us low hydraulic conductivity. Okay, so there is a compromise between cost and the constructability. Okay, so for that, these are the factors that are controlling hydraulic conductivity, the type of soil that you need for the compacted clay liner. Okay, so minimum technology guideline is a little vague on what is the exact value of plasticity index that we need, what is the exact value of type of soil we need, right? Mostly it says, okay, CL is fine. There is nothing called medium plasticity clay for USCS classification system. For that reason, either we have low plasticity clay or high plasticity clay. Okay, so low plasticity clay is fine, high plasticity clay is fine, silty clay is fine, provided that gives us enough low hydraulic conductivity. So, for example, this is only example, like Majore's specification for subtitle D soil liner is like that, you see. So, when we design soil liner, sometimes what we do is we set up, we go to the field, we get the soil sample that we are using, and we are compacting there with the same compaction effort, and we are running the field test there for hydraulic conductivity. We are running the field test to see how the leach travels, how the fluid travels from top to the bottom of the liner. So those type of testing environment in the actual landfill site are called test pads. So if we are using test pad, that is better because we know what's going on in that type of soil. Okay, so if we have test pads, then it is always good to have CL, CS, or SC. So even though we don't have test pad, it's fine. The CL, CS, or SC are typical type of soil that we will be using for the compacted clay liner. But only difference now is if we have a test pad, then percentage of fine, if it is more than 30, it is fine. Okay, but if there is no test pad, that means we did not actually test the hydraulic conductivity. Okay, in field. For that reason, everything is our assumption. For that reason, we prefer higher percentage of fine in it. So if you recall what we talked before, you see that higher percentage of fine, more than 50%, was almost enough for the both ranges of hydraulic conductivity, both ranges of those upper and lower limit to get the hydraulic conductivity of -7, 10 to -7 centimeter per second. Okay, so that's the reason we want to be in little safer side if we did not make test pad in the field and test the field hydraulic conductivity. Okay, so if we have test pad, liquid limit should be more than 20. Plasticity index, and no test pad, mostly liquid limit, we don't worry too much because that liquid limit value is controlled by the type of soil we have here. But plasticity index, if we have test pad, if the plasticity index is more than 10, and of course, if that plasticity index gives us hydraulic conductivity to the 10 to the -7 centimeter per second, that's fine. That's okay, right? But if we don't have test pad, then we have no idea what will be the hydraulic conductivity of the actual soil. We are just thinking, we are just assuming based on our statistical data. For that reason, we prefer the plasticity index ranging from 15 to 30. That way, it can be covered in the wider range. Okay, so the bottom line for us is to get the hydraulic conductivity 10 to the power -7 centimeter per second. So if we have test pad, we can test them. Okay, so if the hydraulic conductivity that we are getting in the test pad, where we use the same soil that we are planning to use and same compaction effort we are using, if it does not give hydraulic conductivity 10 to -7 centimeter per second, less than 10 to the -7 centimeter per second, then we can't use that. Right? But for no test pad situation, we have no idea what type of soil is this, and for that reason, mostly we are just estimating that if the soil has percentage passing more than 50% and the plasticity index ranging from 50 to 30, that will give us hydraulic conductivity less than 10 to -7 centimeter per second. With that assumption, we go with the percentage fine and the plasticity index only. Okay, so in the test pad, we compact that with 95% of standard Proctor. We'll talk about Proctor compaction here. So it's maximum dry density we can get with certain compaction effort is called maximum dry density from the standard Proctor. If we are using standard Proctor energy, that we'll talk about that in a while. Okay, so in the field we are expecting 95% of the standard maximum dry density that we got from the laboratory standard Proctor test for that soil. Okay, and if there is a test pad, and we prefer that the moisture that we are using to mold the soil is ranges from the moisture content that gives us maximum dry density in the lab, that is called optimum moisture content, to optimum moisture content plus 4%. So the wetter side of the optimum moisture content is always favorable for the compacted clay liner. We'll talk about that, why it is the case in a while. Okay, so percentage of particle more than 2 millimeter. So this is more than 2 millimeter gives you still sand based on USCS classification system. But if you use other classification system, sometimes people call it fine gravel or something. So that's the reason. So the meaning is large size particle. So if you have test pad, no specification, because we are testing all these things. and after we got enough hydraulic conductivity, we're fine with that. But if there is no test bed, we don't want to take risks, so we limit the percentage of the particle more than 2 millimeter to less than 10%. Okay, so this is the specification for Missouri. It could be different for California. It could be different for different part of the world. So the other characteristic that controls the hydraulic conductivity is freeze-thaw environment. So it is extremely important, and it plays a huge role in major part of the U.S. where we have the frost depth. Right? For California, for Southern California, for Los Angeles, we don't have frost depth. But if you go to northern part of the country, like the North Dakota or Wyoming, then the annual freeze-thaw zone, depth of the annual freezing zone is pretty large, sometimes even higher than 5 foot. Okay, so that freeze and thaw cycle. So in winter, the ground freezes. In the summer, the ground and then the frozen soil melts and thaws, and that will cause a big problem. Okay, so that freezing and thawing cycles may cause more than 3 order of magnitude increase in hydraulic conductivity. The main reason for that is when soil freezes, then the volume of the water increases. That way, the void space that is filled with ice increases because the water becomes ice. So void space filled with ice that is volume of that void space increases, right? And then when it thaws, it becomes water. For that reason, the actual volume, with different number of cycles, the actual volume of the void keeps on increasing. So higher the volume of void you have in the soil sample, higher the hydraulic conductivity. So for that reason, ice lenses will increase the volume and increase the porosity of the soil, right? Once the porosity increases, the hydraulic conductivity increases. That's the main reason. The freeze-thaw cycle increases hydraulic conductivity, and we have to apply caution when we and we have to consider all these facts when we design the compacted clay liner in the area where we have freeze-thaw potential. Okay, the changes in hydraulic conductivity that take place typically during the first 3 to 10 cycles. It is most significant that during those cycles the most significant alteration takes place. Okay, so these are typical controlling cycles, 3 to 10, but always the first freeze-thaw cycle will cause more variation in hydraulic conductivity compared to the because that will squeeze the soil in. Okay, so that will increase the volume of the ice and so the soil in continuously. So first cycle is more important than 10th cycle. Okay, so most of the significant changes, as I told you, happens in the first cycle, and with the increase in number cycle, the change in hydraulic conductivity with freezing and thawing action reduces. Okay, so it's always good idea not to let the compacted clay liner exposed over the winter. Okay, so what we do is we cover them, right, and we do more compaction right after first winter. You see, the thing is so we know freezing and thawing, we cannot control it, but as soon as one cycle of freezing and thawing is done, we compact again. That way, even though the void space is increasing, by compacting we reduce the void space. That way we maintain the hydraulic conductivity. That is one remediation in those areas. Okay, so we talked about the compaction. You see, when we compact soil, okay, so we take the soil in it could be a soil in the field, real field, and compact with compaction devices, or you can take a soil in a container, let's say in a steel container, pour the soil in and drop hammer to compact them. Okay, the compaction effort increases. What is the objective of compaction? To increase the density of the soil mostly. Okay, so if we add water in it, that water will help to move the particles inside, fill in the voids, reduce the void space, increase the density. Okay, but For that reason, more the water we are adding, that will lubricate the soil, that will help the soil to move closer, and that will be helpful to increase the density. But if the amount of water is more than certain amount, then that water, the amount of water required to help that action of the movement of the soil easily with the lubricating effect, if we add water more than that, then that excess water may end up filling the void space, and when we are compacting, then the water may repel the inertia back. One thing. Second is water is incompressible, so that will take the void space that has potential to be compacted. Okay, so because the void space is taken by water, water is less dense, the specific gravity of water is much less than the specific gravity of the soil, then that will start reducing the density of the soil. So up to certain amount, certain percentage moisture content is always good to during compaction effort to raise the dry density. After that effort, that amount of water, then water plays negative role. Okay, in terms of the maximum dry density, but we'll talk about that in detail in the next couple of slides. Okay, so for that reason, compaction effort controls the hydraulic conductivity. More the compaction effort, you see, more the water content and higher the density of the soil, lower the hydraulic conductivity for same type of soil. Okay, so in a compacted soil, even within the compacted soil, the hydraulic conductivity depends on the water content during compaction. And also the method of compaction will deal with that, you see. So you already saw that water content higher density we get, and the lower the void space and lower the hydraulic conductivity, right? And up to certain location that works. And depending on if you increase the amount of inertia, then even with less moisture content, you can increase the dry density of the soil or dry unit weight of the soil, right? We'll talk about that in a couple of slides. And the important thing for us is to know what is the moisture content that corresponds to the maximum possible dry density of that particular soil for that particular inertia effort that we are using. Okay, that corresponding moisture content is called optimum moisture content. So optimum moisture content is the moisture content of the soil that gives us maximum dry density or maximum dry unit weight. Okay, so now you see this figure you have is exactly same figure than the one that I showed you before. Higher the moisture content, molding moisture content, higher the dry unit weight or dry density of the soil. So the broken line you can see here is the moisture content that corresponds to the maximum dry density, which is optimum moisture content. Now if you see the hydraulic conductivity of the soil, you see the hydraulic conductivity at that moisture content is somewhere here, right? If you increase the moisture content, higher the moisture content, then the pore space is filled with water, right? And then even though the density is little low, hydraulic conductivity decreases. Okay, so hydraulic conductivity becomes almost constant at this particular point. At the moisture content, higher, certain percentage higher than the optimum moisture content. We'll talk about that, optimum moisture content. So increasing the moisture content beyond that does not reduce the hydraulic conductivity. You could see that is almost constant. But the disastrous thing is that reduces the dry unit weight of the soil. So lower the dry unit weight of the soil, higher the void space in the soil. So there is a risk that the water that we have inside get evaporated, and then that will create trouble in future. Okay, so we don't want to take that risk. So the soil is compacted always. For this reason, it is always compacted to weight of optimum. That is, moisture content higher than optimum moisture content is called the weight side of optimum. So if you see this figure, anything on the right side is called weight of optimum, and anything in the left side is called dry of optimum. So we always in the landfill side, we mostly we keep the moisture content in the weight side of the optimum. Okay, so that has a 2 to 3 order of magnitude smaller hydraulic conductivity compared to the dry order of maximum. You see the hydraulic conductivity to this side is much lower than the hydraulic conductivity, much higher than the hydraulic conductivity in this side, or right side. So right side is always 2 to 3 times, even more lower than the left side, that is dry of optimum. So we have to keep that in mind. For that reason, when we make this specification, we always tell that, okay, the field moisture content that we use to compact the clay liner should be more than the optimum moisture content, or should be in the wetter side of the optimum moisture content, but we don't want to go beyond certain moisture content. That does not help us reducing the hydraulic conductivity. We have to keep that thing in mind. Okay, so the other factor that controls the hydraulic conductivity is the way how we compact the soil. Okay, the clays are compacted, can be compacted in 2 ways. Okay, so one is the we lay the soil, let's say 6-inch thick soil, we call that lift. Okay, 6-inch lift of soil, and then we roll the soil with a smooth wheel roller or some static compaction on top of that. Okay, so that's one way we compact the soil. The other way to compact the soil is we do kneading. So kneading is like, you see, static compaction is just simply put a pressure on top of that and let that pressure cause the reduction in the volume of the soil to increase the density. The other is kneading action. You see, when you are making you're adding water in clays, more kneading you do in the clay, more distribution of the water you can get at one point. At the same time, if you have a device that has that kneading action, that means it is mixing the soil, so it is compacting the soil at this point, at the same time it is compacting the soil at this point at the same time. That is called kneading action. Okay, we need to have projection. That way you are applying similar pressure at the bottom, similar pressure at the top. But if you do static pressure, you have more pressure at the top, little less pressure at the bottom. So if you have kneading, that kneading action makes sure that the soil is uniformly compacted in all area. Mostly it is important for clays. So kneading type of compaction will reduce the hydraulic conductivity significantly compared to the static compaction if the moisture content is more than certain amount of moisture content. Okay, that's important. And we need the, let's say this is the optimum moisture content, right? And at the dry side of optimum, it does not make a big difference. Whatever way you are compacting may give you the similar result. But if you go to the wetter side of optimum, right? For example, this 18% here. If you go to about 21%, so 3% more than 18, right? What you could clearly see is hydraulic conductivity that you get from the soil that is compacted with kneading. We'll talk about that. You need shift-footed roller for that. By kneading action, right, with a projection, that way you have compaction at bottom and top at the same time, and that hydraulic conductivity is almost 4 or 5 times lower than the hydraulic conductivity that you get from the static compaction effort. So it's extremely important for us to know. So mostly for clays, we prefer to use shift-footed roller. The main thing for that is it does kneading compaction as opposed to the static compaction. Okay, so both kneading and impact compaction yield lower hydraulic conductivity than does the static compaction. Impact compaction is we drop something from the top. Nowadays, you know, that dynamic compaction is more common term, and it is quite popular in the transportation industry. So anything that provides impact. So one example of impact compaction is like in the lab, we just drop the hammer from certain height. It is impact compaction. So impact is better than simply static compaction, where you simply put the static pressure. Okay, so most of the specification, but you know, the issue here is most of the specification, lab specification, people prefer the static compaction. So those static compactions are suggested, compaction efforts are suggested for the lab specimen mostly. The reason for that is, you see, in the lab, you are making sure, if you take the soil out, you are making sure that for that compaction effort, the soil, how much hydraulic conductivity that you are getting. So we compact that with static compaction to bring it to the density, required density, right? And then we run the permeability test. in the lab. So that will give us what is the hydraulic conductivity of the soil for that soil at that optimum moisture content, and that that moisture content and that required dry density. Okay, and then after running the permeability test, you see what will be the hydraulic conductivity of the soil. So in the lab, you may, then in the field, if you are doing, in place of a static, if you are doing kneading compaction, definitely we can get lower hydraulic conductivity, right? That way, in the field, in the lab, we make sure that the hydraulic conductivity that we are getting for this compacted clay liner is 10 to the power 10 to negative 7 centimeter per second. Right? So if you are getting that in the lab, in the field someone is doing kneading compaction, then definitely that will give us hydraulic conductivity lower than that, so we are the conservative side. So but we don't want to do opposite. You see, if you do kneading compaction in the lab, right, and then that gives you a hydraulic conductivity lower than 10 to negative 7 centimeter per second, and in the field we are using static compaction, then that is disastrous. Right, so to be on the safer side, always we prefer to do the lab test on this static compaction. So okay, so a higher degree of compaction always reduces we do higher degree of compaction, that means we increase the dry density with lower moisture content. Okay, the benefit of that is that would reduce the because the dry density increases, right, and then the void space reduces, and because the void space reduces, the amount of water going, or the leachate going, fluid going into that void space reduces, and then the contact with the soil, the possibility of having the surface of the soil to be contacted with that the contaminated fluid reduces, and that reduces the possible change in property of soil due to the contamination with the chemical, due to the chemical attack into the mineral that we have in the compacted clay liner. So this is important. Okay, so one thing we have to keep in mind is hydraulic conductivity. The actually compacted clay liners, they are not fully saturated. Okay, when we operate that in the field, they are not fully saturated. Okay, so when they are in the field, they are not fully saturated. Okay, they are compacted. Compacted means degree of saturation less than 100%. We'll talk about that. Okay, so that means you have air void, and you have the water void. So the conductivity of the water is called hydraulic conductivity. Conductivity of air is not called hydraulic conductivity. It is called the coefficient of permeability of air, or coefficient of air permeability. Okay, so if we put the soil sample in the lab and saturate it and measure the hydraulic conductivity, okay, that is called let's say that is hydraulic conductivity for saturated phase. So if the degree of saturation is 100%, yes, E is 100%, right, and the hydraulic conductivity divided by this KRA or KRW is relative hydraulic conductivity. So hydraulic conductivity of that soil, okay, divided by the hydraulic conductivity of the saturated soil. So because it is completely saturated, hydraulic conductivity of that soil divided by hydraulic conductivity of the saturated soil will be 1. Because mostly when we run the hydraulic conductivity test in the soil, we saturate the sample and measure the hydraulic conductivity of the saturated soil specimen. Okay, so that will be 1. But in reality, the soil is not, the compacted clays are not saturated. Let's say degree of saturation, that means percentage of the void filled with water, void space filled with water is, let's say, 80%. This is typical in compacted clay soil. Okay, then your actual hydraulic conductivity is only 40% of the saturated hydraulic conductivity. Okay, we have to keep that in mind. Okay, if we talk about hydraulic conductivity of air, the permeability of the air is much lower than the permeability of the soil is different than the permeability of the soil. The permeability of the air is totally different than the permeability of water, right? So if we talk about the hydraulic let's say permeability of the air flow, right? So when there is no water in it, that is, everything is air. So degree of saturation is 0%, right? And then the hydraulic, the permeability of the air would be almost 100% of the permeability of the air when it is dry, right? Hydraulic, the permeability of the entire soil specimen is equal to permeability of air. Okay, and then slowly when we add water in it, the permeability decreases significantly, right? Because permeability of water is much lower than the permeability of the air. So these are the functions that we are looking for. Okay, so mostly bottom line from this figure is if the soil is partially saturated, let's say 80% of the void space is filled with water, then the hydraulic conductivity is only 40% of the hydraulic conductivity that you are getting for the saturated sample. So it takes longer time for the leachate to travel down. Okay, so for that reason, degree of saturation controls the hydraulic conductivity. Okay, if the soil sample is not saturated, its measured hydraulic conductivity is, when we talk about water, we call hydraulic conductivity. So its measured hydraulic conductivity increases with the degree of saturation. Okay, so we have to keep that in mind. Okay, and then we always check that in the relative permeability curve like that. We check the ratio between the hydraulic conductivity of the soil. Rw is hydraulic conductivity. Ra is the air conductivity, air permeability. Okay, so we always need to use this type of chart for different type of soil. Okay, so the other thing that is controlling the hydraulic conductivity of the soil is hydraulic gradient of the soil itself. Okay, so what we saw was what EPA requires is, it requires the height of the leachate in the landfill should be less than 1 foot, that we talk frequently. Okay, so let's say the thickness of the clay liner is 1 foot, and the thickness of the leachate is height of the leachate is 1 foot. That gives us the hydraulic conductivity is equal to, hydraulic conductivity is head difference, right, divided by the length it traveled. Okay, so if the head difference is pretty high, then hydraulic gradient will be high, because let's talk about, let's go to differences. If the thickness of the liner is 1 foot and the height of the leachate is 1 foot, then the hydraulic conductivity is H, if you recall the equation we could talk before, H plus D over D. So that is total 2 foot over 1 foot. Hydraulic conductivity is, hydraulic gradient is 2. Let's say you have a liner 3 foot thick, right, and the leachate is 0.5 foot tall. Then now it will be 3.5 over 3. That is much closer to 1. So we always try to reduce the hydraulic conductivity and to put it closer to 1. If you reduce the thickness, right, then the hydraulic gradient increases. So we try to keep hydraulic gradient close to 1. It is impossible to have exactly 1, but closer to 1. Okay, so we want to increase the value closer to 1. That will be our objective, right? So for that reason, we limit the height of the leachate. So hydraulic gradients in the field are much lower than the hydraulic gradient that we get in the lab. I mean, for a reasonable time period. The reason for that is, you see, what we assume is, when we calculate the hydraulic gradient, we assume that water is moving from height h in the filter zone, the drainage layer, all the way through the compacted clay liner. So hydraulic gradient we are calculating is equal to H plus D. That is, H is height, thickness, height of the leachate, and D is the thickness of the clay layer. But water is not percolating. This is the worst possible situation when the leachate travels all the way down from the clay liner, through the clay liner. So we don't want that. Most of the time what happens is it takes forever, or maybe several years, for that water to travel from, or maybe may not be traveling at all, from the top of the clay liner to the bottom of the clay liner. So that means the high H value, delta H value, that is the head difference value, is lower than the head difference that we are calculating. So the thickness of the clay layer is same. So because the head difference immediately after the construction of the landfill, let's say, the head difference is much lower than the head difference that we are calculating, because in the head difference, in our calculation, we are calculating head difference is equal to, with the assumption that the leachate travels from the top to the bottom of the clay liner. That never happens. Okay, so we are in the conservative side. So the high gradients, always higher hydraulic gradients, results in larger effective stress. That is true, because the higher gradient impose higher seepage pressure. Okay, higher the seepage pressure, that means soil is pressing, so that will cause, you see, the upward pressure is called negative pore water pressure. I mean pore water pressure, upward pressure. Okay, that is opposing the effective vertical stress, opposing the vertical stress we are getting in the soil, right? So, but downward gradient. So, if this water is moving downwards, then that will add into the total stress that, I mean, stress that we are getting from the overburden pressure of the soil and the landfill, the refuse or something. So, if the downward seepage, downward pressure of the water always adds into the surcharge pressure, that will add, you see, the stress that you are getting, total stress you are getting, the effective stress you are getting is total surcharge stress plus the water pressure, right? So water pressure, when the water is moving up, when you have earthquake load, is negative. That is acting opposite to the gravitational force. But when water is seeping down, this will act in the direction of the gravitational force, so that will add in a certain amount into the effective stress. We have to keep that in mind. Okay, seepage pressure will going down when the water is going down, or leachate is going down, or fluid is going down. That will increase the effective stress. Okay, so that causes the change in the volume of the specimen, because if you recall your consolidation, higher the effective stress, then you have compression in the soil. Okay, compression means if it is completely saturated, we use the word consolidation. Soil gets consolidated, and then that will reduce the volume. Okay, and then volume reduces, definitely the void ratio decreases. Okay, so you have to keep that in mind. So high gradient also causes the migration of the soil particles that may cause either clogging, because high gradient means high energy, right? So there is a possibility that with that energy, with that pressure, the suspended particle may forcefully travel from the pore space, right? And that may clog the soil we have in, right? And then if it clogs the soil, then the pore space, if it goes into the pore space, right, and then that will increase the pore size, right? Once the pore size increases, then you know, the finer the soil, more finer the pore space, right? So if the pore size increases, and that will increase the, eventually that suspended particle will flush out at that point. Then if that suspended particle is flushed out, then the pore space increases. Okay, that's important to note, and that will increase the void ratio of the soil. Okay, so, and consolidation stress, that is the pressure we are giving to the soil. At some point when the compacted clay liner is completely saturated, then first we put compacted clay liner, right? And then at one point you have that huge amount of leachate on top of that. So portion of the compacted clay liner might be completely saturated. So when the portion of the soil is saturated, and then we keep on putting garbage on top of that, we are increasing pressure on top of that, right? And that increase in pressure will cause, will squeeze the soil. It will compress the soil. It will press the soil, right? And then the water gets pressurized, and that pressurized water starts leaking out, getting out. So the water will drain out. That phenomena is called consolidation. Water will drain out, and that will reduce the volume of void. That will reduce the void ratio. That phenomena of draining the pressurized water or fluid out from the void space to reduce the void ratio and the volume of the soil is called consolidation. So higher the consolidation. How do you get consolidation stress? More garbage you are putting in, that keeps on increasing the consolidation stress. That is the pressure that is pushing the compacted clay liner, right? Higher the consolidation stress, lower the K, because that will increase the, that will reduce the void ratio, that will increase the density, that will reduce the void ratio. Okay, that will reduce the volume of the void, and that will cause reduction, because the void ratio decreases. That will cause reduction in hydraulic conductivity. And we are in safer side, because if we are talking about the hydraulic conductivity of the soil before consolidation, right, and then we are in safer side, because as the stress increases, the hydraulic conductivity decreases. But we have to keep in mind that thickness of the clay layer also decreases at the same time, because the volume decreases, right? So with that reduction in volume, thickness decreases, and the travel path decreases, okay, and the travel time decreases. We have to keep that in mind. But there is a compromise. All the time we need to run all calculations to check what's the best for us. Okay, the permeating chemicals we have, because you cannot control the chemical quality of the leachate flowing down. It depends on what type of garbage you have. Okay, so permeating chemicals, they can significantly change the hydraulic conductivity, mainly because they can alter the property of the soil, chemical property of the soil. As I told you, when in the past, you see, when we pass calcium chloride from the sodium marmolite, which is highly expansive clay that gives you much lower hydraulic conductivity. When we pass calcium chloride salt from that sodium marmolite is converted into calcium marmolite. Now calcium marmolite has much lower liquid limit and much lower plasticity compared to the sodium marmolite. So that way the characteristic changes, hydraulic conductivity changes. And sometimes even that's mainly because of the change in the double layers. Double layer is the layer between two plates where you have free cations and freely moving, okay, in the electrolyte system. That the thickness of that. Higher the thickness of that, lower. Higher the thickness of that, higher the plasticity of the soil. Okay, so but if that decreases, then the soil, the attraction between one plate to the other increases. That means there is a possibility that one soil plate will merge with the other soil plate pretty easily, because they have huge attractive force, and that way the particle shape changes, right? Once the particle shape and the fabric changes, then that will change the hydraulic conductivity. So we have to be very careful. Okay, so we have to think of what type of chemical we are getting from the leachate, and what will be the reaction of those chemicals, or if you have acids or bases, what will be the reaction of those with the soil we are using for the compacted clay liner. Okay, sometimes what happens is some chemicals just produce the precipitation. Like if you have lime, if you have calcium, that can produce the precipitation, calcite precipitation, right? Once you have calcite precipitation, that becomes solid, and that will take the pore space, right? And that will take the void space and block the void space because of that precipitation, and that means that will block the movement of fine. Okay, and the other possibility is if there is a movement of fine and if there is a movement of water, and sometimes what happens in long run, there is a possibility that depending on what type of chemical you have in that water, there is a possibility what type of biological characteristics you have in that soil, there is a possibility that at one point you may also develop microorganisms. So if microorganism is developed, that microorganism will take the space of the void space, so void ratio reduces, right? And it's okay, void ratio reduces, but sometimes if that microorganism is gone or something, then void ratio returns back to the original or even becomes bigger. And we have to keep all those things in mind. So permeating chemicals, the chemical composition of the leachate can cause a change in hydraulic conductivity. Okay, mostly if those the precipitation or microorganisms are developed that reduce the hydraulic conductivity, maybe in a positive side, but sometimes if you have salt, different type of salt like calcium chloride and those things, that will reduce the hydraulic conductivity. That will increase the hydraulic conductivity because that will increase the soil fabric size. Okay, higher the particle size, higher the hydraulic conductivity. Okay, so it's always important for us to run all those tests even in the lab situation for the potential contaminated mostly it is artificially prepared contaminated water. We'll talk about that in a couple of weeks, how we prepare that type of soil solution, but it's all the water solution, which is always good to test the water with different chemical components and see how those chemical components change the hydraulic conductivity of the soil that we will be using. Okay, so the important variables that we need to consider in testing hydraulic conductivity in the lab are like that. You have to make sure that always the lab sample may not be same as the field sample. So we have to make the field sample, lab sample, as close as possible to the field possible sample, because field compaction is done by the sheaf foot roller. It could be done by the smooth foot roller, any type of roller. Lab compaction is done by, let's say, if you are using static pressure, or lab compaction may be done by by dropping the Proctor hammer, right? So we have to keep all those things when we set up the lab environment. So we always try to make the lab sample as close as possible to the field sample. Okay, and always degree of water saturation is extremely important. So we talked about that. Higher the degree of saturation, higher the hydraulic conductivity. We saw that. For that reason, to be in a safer side, if you run all tests with the 100% degree of saturation, that'll give you the maximum possible hydraulic conductivity, and we are in the better side, or the conservative side of the design. Okay, stress condition. We have to keep that in mind. What is the stress that we are putting in that sample to simulate the field situation? Because the effective stress in the field ranges from day one to the end of to closing. Effective stress ranges significantly. Okay, so from the starting to the end of the landfill site or the sale. Okay, so we have to make sure that the hydraulic conductivity is maintained to the required hydraulic conductivity for different stress ranges. So we prepare the sample by compacting that at different stresses that is potential stress in the field, and then run the hydraulic conductivity test on that. Okay, there are different ways we run hydraulic conductivity tests, and we'll talk about that. Okay, and also important to see the confinement condition. Most of the time when we talk about lab hydraulic conductivity test measurement, we are confining from the side. That way everything is one-dimensional, right? In reality, in the field, you have huge horizontal stress coming. That is the confinement. If you have certain vertical stress coming at certain point, then depending on what the friction angle of that soil, then you can get certain amount of horizontal stress also coming to the soil. So that confinement condition in the field might be different than the confinement condition in the lab, but we have to try to make that confining condition also into effect into our calculation or into our conclusion or recommendation when we talk about the design for the field. Okay, and we also need to write the testing detail. That way a design engineer will figure out what was the condition where the hydraulic conductivity of 10 to -7 or 10 to -8 was obtained for that soil. Okay, it is important for us to note all those things when we submit the report of the lab hydraulic conductivity test. Okay, but there are so many limitations of the lab test because field situation is totally different than the lab situation. One big example is in lab we are doing one-dimensional test, while in the field where the permeability is acting in all three dimensions. The soil is sheeping, or soil is transferring from one place to moving from one place to the other. Water is seeping, or water is moving from one place to the other in all three dimensions. Okay, so a couple of limitations that we have from the in the lab tests are: first, non-representative samples. So it is almost impossible to get exact same sample as we get in the field, because mostly all these things are done before we start constructing the landfill site. Okay, so that's the thing we need to keep in mind. And there may be possibility in preparing the problem in preparing the sample size for the lab test. Okay, so in other words, while we are preparing, we may not be able to make the homogeneous sample. There is a possibility there is small portion that is heterogeneous, and the hydraulic conductivity of that portion is much more or much less than the hydraulic conductivity in the other side. That will affect the result of the lab test data. Okay, and also in the field, mostly in the lab, mostly our the flow is vertical. Okay, we do one-dimensional hydraulic conductivity test that we will see in a while. And in the field, there is a possibility that you have vertical, and all of a sudden between the contact between two layers, you may have horizontal hydraulic conductivity more than the vertical, then water will seep horizontally, right? So and water can seep in any direction during the lab test, during the field, but in the lab test mostly we do vertical. Okay, and then alteration in the clay chemistry. In the lab we do mostly either we do with the distilled water, or we do with certain amount of the leached water simulated or maybe prepared with certain amount of possible the chemical composition in the field or biological composition in the field. But in the field we may end up having totally different leachate than that, because we just estimate what type of garbage we are getting, what type of water we may leachate we may end up getting after dumping those garbage. But these are all our estimations. The actual garbage we dump into the site, actual solid waste we dump into the site after the compacted clay liner is done. Okay, so that may change the property. And in lab we don't have much time to develop microorganisms. In the field there's a possibility that microorganism may develop. Okay, and the amount of air in the sample in the lab, mostly we do the lab test in a saturated situation. That way we are in conservative side, right? And we assume it is completely saturated. And there is a possibility that it may not be saturated, but in the field definitely, the degree of saturation changes from certain percent, maybe 60, 70, 80% to 100% with the passage of the time. Okay, and then in the lab we may end up using excessive hydraulic gradient to reduce the testing time, because higher the hydraulic gradient, lower you can reduce the testing time, because more discharge of water you're getting, right? In the field, you are the hydraulic gradient or the hydraulic gradient or the head difference is mainly determined by the amount of leachate generated. So there is a difference, and because we are increasing excessive hydraulic gradient in the lab, that may cause a huge volume change or significantly high volume change due to the effective stress change when we increase the hydraulic gradient. Because higher the hydraulic gradient, higher the seepage pressure. Higher the seepage pressure, higher the effective stress. Okay, for that reason that may cause volume change. That effective stress may cause volume change within the lab test, which may be different in the field. Okay, so definitely temperature makes a difference, and nowadays our main concern is elevated temperature in the landfill sites. Okay, so there are huge difference in temperature between the environment, outer environment, and inside the landfill site, because there are so many chemical reactions going on inside landfill site after we dump the garbage. Okay, so those elevated temperature may cause the change in hydraulic gradient of the leachate. In the lab, we run the test for laboratory temperature situation. We cannot simulate that high temperature in the lab situation. Okay, so how do we measure the hydraulic conductivity in the lab? We'll go through it a little bit. So one type of test is it is important for us to note the degree of water saturation first, right? So dry soils are less permeable than the wet soil. We already talked about that, right? So they're mainly because the permeability of air is different than the permeability of water. So the invading water only flows through the water-filled voids because it needs to have continuation of the water. Okay, so some engineers believe that the hydraulic conductivity test on clay should be done in fully saturated situation, and I personally believe that because that will give us conservative the value of hydraulic conductivity. Okay, so that will give us highest possible hydraulic conductivity. We talked about that. Okay, and the main reason for that is the gas can be eliminated by, and how do you make that situation? Let's say you compacted the soil sample somewhere at the field compaction level, and we bring that into our triaxial compression device or a permeameter, and then what we do is we supply water from outside at high pressure. Control, you can supply huge pressure, controlled high pressure. That way, then take the water out. So we keep on supplying water in high pressure until the water from the bottom, until the water comes out from the top. That means if the water is coming out from the top consistently with the same amount, then that clearly tells us. And we also check what the pressure of the water we have at the bottom versus the pressure of the water we have at the top. So it is same pressure. That means you have the soil is completely saturated. So it is little more. You need to learn in more detail on this back pressure saturation, but what we do is we can saturate the soil sample by supplying water from outside, putting the sample in a chamber and supplying water at pressure from outside to saturate that. It is important for clays because clay has very small pore. Sometimes it takes a couple of days and even a week for a clay sample to have complete saturation with those back pressures. And I mean, those who are in 547, that is advanced soil mechanics, you'll learn about this in detail. But those who are not in that, just think that one way of saturating soil quickly, partially saturated soil clays quickly, is by supplying water in pressure and letting the water flow from bottom to the top. Okay, so if you see the effect of confining pressure on the hydraulic conductivity, you see we are talking about clay. So mostly, so if the sample, because clays when they are dry, when they are wet, they expand. When they are dry, they shrink. So when they have that expansion and shrinkage behavior, then you have negative pressure develop. So what they do is the clays crack like that. Whenever you have some pulling effect, when it is shrinking, then one soil is pulling against the other. So right, when they are trying to separate from each other, and then because of that, tension is created. Okay, that tension or potential or tension or suction we have, that suction cause the soil cannot take tension. So what happens? The soil cracks immediately after it has tension. So when you have that tension much below the ground, that tension is balanced by the effective vertical stress. So you don't have negative effective stress, the total vertical stress. That way you don't have negative effective stress. But on the surface of the soil, what happens is you don't have much surface load, so soil cracks. Right? These type of cracks are called desiccation cracking. So soil cracks when they get desiccated, when they get the moisture content reduces. So if you have that type of this type of desiccation crack, you can see in this picture, then what happens is the void space you have is so heterogeneous. At the same time, those void spaces are so big compared to the void space you actually get into the soil. So when you have that situation, your hydraulic conductivity will be significantly high, right? And how do we reduce that situation? What happens is, if we increase the confining pressure, if you take the soil and if you push the soil from the side, then what happens is, with higher the pressure you're applying, lower the size of the pore space you get, or lower the size of the crack, because the soil now again come closer to each other. Okay, so if you see that, if you have a sample that contains desiccation cracking, and if you increase the confining pressure before you run the hydraulic conductivity test, then with higher the confining pressure, significantly low hydraulic conductivity, because the void space is filled, or I would not say filled, it is reduced. Okay, the size of the crack reduces. Okay, if the sample does not have that desiccation cracking, then what happens is, yes, if you increase the pressure from the side, that will reduce the void ratio. Because of that pressure, void ratio decreases. If you pressurize something, the soil get consolidated or compacted, right? And then the void space decreases. That will reduce the hydraulic conductivity, but not as significantly as you can see in the soil that has desiccation cracking. So in the field, you have similar situation may end up happening. Okay, so sometimes it's disastrous to have high confining pressure when we run the laboratory test, because that may end up giving us false result of the hydraulic conductivity, or unconservative result of the hydraulic conductivity. Okay, so it's always important for us to figure out what would be the stress and confinement conditions in the field, so we can estimate that and we can apply similar confinement level when we run the test. Okay, so for example, 1 foot of soil has about 1 psi of overburden. It's not exactly 1, it's slightly less than 1 pound per square inches of the stress, right? So because gamma of the soil, let's say, is 120 pound per square foot, and if you multiply that with 1, that give you about the vertical stress of overburden pressure of about 120 pound per square foot, right? 1 pound per square inch is 144. 1 pound per square inches is 144 pound per square foot. Okay, so for the identical soil near the ground surface should be more permeable and more porous, because as I told you, confining stress is dependent, is proportional to the overburden pressure. Higher the overburden pressure, higher the confining stress, right? That ratio, the proportionality coefficient depends on the friction angle of the soil. Okay, so at the top you have less confinement because less overburden pressure. At bottom you have more confinement and more overburden pressure, right? So you have to keep all those things in mind. Okay, this makes the soil at the top more permeable than the soil at the bottom. Okay, we have to keep in mind. So also one thing we have to think is, mostly clays have plates. Okay, because they have plates, when we are compacting with high inertia, there is a possibility that the plates are elongated, right? If they are parallelly oriented on top of that, like your stack of plates, then the vertical permeability is always less than the horizontal permeability, because in contact between those plates, in contact between layers, then you have higher permeability compared to the vertical one. Okay, so that will cause the soil anisotropically soil to have anisotropic property in terms of hydraulic conductivity. Okay, so all these factors we have to keep in mind when we design the landfill site. Okay, for that reason, the confining stress used in the lab test should be of the same magnitude as that in the field. Okay, the reason for that is magnitude of confining stress changes with overburden pressure, and the overburden pressure changes with time. So rather than fixing into one, we may want to see the ranges. Okay, so for example, oil reservoir cores, you see they are much more below the ground. When you take them out from the ground, then now you see overburden pressure was thousands psi when they were under the ground, right? When you take them out now, no overburden pressure, soil expands. Okay, so these are important things for us to mind. to keep in mind when we design the lab tests and when we design even the landfill sites. So bottom of the liner will always receive additional compaction from the waste and final cover that we talked before, right? On the other hand, none of these things exist for the top cover. You see, so bottom get more confining pressure, more overburden pressure compared to the cover. Okay, so liner gets more overburden pressure than the cover, because the only thing that you get on top of cover are topsoils. Okay, in addition to that, the cover is the cover is that is top. After you're done with your landfill, you cover that with a layer called cap or cover. So the cover is subjected to many environmental forces. Now you have erosions coming. If you have huge rainfall coming, that may cause erosion, right? So and then in dry, you have more desiccation cracking problem in the cover compared to the liner, because mostly top portion of the liner is filled with leachate anyway, so it is getting saturated with leachate. But if you talk about the cover, then depending on wet season, it gets a little wetter, but mostly the temperature changes called desiccation cracking on the cover. So it is extremely hard to design and implement a final cover with a hydraulic conductivity lower than that of the bottom liner, because yeah, in reality you may come up with that, but in practice, all those environmental consequences may cause the increase in hydraulic conductivity in long run. Okay, so how do we run the hydraulic conductivity test? We just compact the soil in a mold. It is called rigid wall permeameter or container. We compact the soil inside at certain pressure, we lock them, and then we flow water. Okay, so if you have time, come to my lab and see. I have different type of permeameters, then you can see all of them in the lab. So these type of permeameter mostly are, the one I have in lab is a little different, but mostly we use this one. This is 4-inch diameter and 4.1 inch, 5-inch tall sample you can put inside. The one I have in lab is 6-inch tall. Okay, so it doesn't matter. What we do is we fill water in here, we make it saturated, and we maintain the head of water. Sometimes we don't maintain, depending on what type of soil we have, but it is a graduated jar, so that way you can see how much the amount of water going down and coming out from the, so it is going down and it's coming from the inlet here, and then water comes out from the outlet, and we measure the quantity of the water coming out depending on the situation. Or we can also use the flexible wall permeameter. Okay, so in flexible wall permeameter, the soil is confined by a thin flexible, mostly they are latex membrane, but we let them expand in horizontal direction. Okay, so that confirms to irregularities in the sample. Okay, so the rigid one is, it has size fixed. So mostly we have two different types of tests. So if we are talking about the filter layer or the drainage layer, we run constant head permeability test. When we talk about the clay liner, we do falling head permeability test. Okay, so the constant head permeability test, what we do is we collect the amount of water coming out at certain time. That'll give us discharge, and the discharge is KIA. K is hydraulic conductivity, I is the hydraulic gradient, and A is the area of the soil specimen. That way you can back calculate hydraulic conductivity. In falling head permeability test, you cannot get sufficient amount of water within limited time period. So there is a possibility evaporation may be more than even the water coming out. For that reason, what we do is we put the water in tiny tube and then fill that, and then at different time period we measure the hydraulic conductivity, the head difference, right? That is falling head permeability test, and we talked about that already. Okay, but we also do field testing, which is much better than the lab testing because it gives you field situation, but it is much more expensive than the lab test. Okay, so field hydraulic conductivity measurement is, field testing is more realistic. It gives you more realistic result than the lab test because the mass of the soil is huge, and the phenomena is two-dimensional or even three-dimensional compared to one-dimensional in the lab, right? So one type of field testing is borehole test. What we do is we drill a hole, okay, and we fill the hole with water, right? And then we measure the rate, and then we keep on, because if you fill that with water, then the water keeps on percolating down from in the ground, right, underground. And then what we do is we keep on filling that hole. That way we measure the amount of water required to fill the hole. That way, amount of water required to fill the hole divided by time period give you discharge. The discharge is, and then based on that discharge, we can easily calculate what will be the hydraulic conductivity of the soil. Okay, that's one way we measure the field hydraulic conductivity in the borehole test. Okay, the other is porous props. What we do is, porous props are similar, but what we do is we take the props. This is like a cylinder filled of mostly they are the porous stones, right? Porous materials made of porous stones. And what we do is we insert them, and then we connect them with a tube, and we supply water in a tube. And then the porous stone let the water uniformly go in the soil space, and we measure the exact phenomena. We measure the amount of water going at percolating down within the given time period. Okay, so we push those porous props into the soil, and we pour water through the the prop, right? So the only thing is, we can, because those props are very small, we can test very small amount of soil with that. And the other one is the infiltrometer test. Okay, so what we do in infiltrometer test is, so we embed certain type of devices we call infiltrometer into the surface of the soil liner. Okay, and then we measure the rate of flow into the liner. Okay, so these are devices. So what we do is, let's say we take a container, let's say solid container, right? And then we put that container, that could be steel container or aluminum container, on top of this the liner, right? And we fill that container with water, and then we measure the height of the water going down with time. Okay, so these type of devices are called infiltrometers, and there are different type of infiltrometer. We have double wall, single wall, sealed. We'll talk about that. Okay, so let's say one way, this is a liner, the hatched one is a liner. So in open the single ring type of infiltrometer, what we do is we fill the liner up to this point with water, right? And then we measure the head going down, height of the water going down, and we, using the formula that we saw before, using Darcy's equation, you can easily estimate what will be the hydraulic conductivity of this liner system. Okay, the problem with this is this is so big that the water evaporates. You have no idea whether the reduction in the height of the water, the height of the water's surface here, is due to evaporation or due to the percolation. So to reduce that effect, that evaporation effect, what we do is we seal them. Single liner, but we seal them, right? And if you are sealing, then what happens is you bury it underwater a little bit, but mostly what we do is we make this tube from where we are supplying water smaller. That way the evaporation becomes less. At the same time, sensitivity of the amount of water going inside increases. Okay, so these are single ring liners, but in the field, double ring liners are more popular. So what we do is we put a bigger liner, large size liner, infiltrometer. We put that in the container first, and then we put smaller size one inside that. The bigger one could be rectangular, bigger one could be the square, smaller one could be rectangular, but mostly we prefer the circular one. Then we put circular inside, and then we pour water inside. So the benefit of that is, you see, now we are controlling almost one dimensional, because it's going almost together, right? So this is confined. The outer rings are confining the inner rings. That way, if we are measuring the reduction in the lowering of the water table, the surface of the water here, that will first, one, it is less evaporation. At the same time, we we are confined from here to here. So here water may go in this direction, water may go in this direction, right? So here this water go in this direction, this water go in this direction, but the water you have in the center has more controlled environment to flow vertically. Okay, so as we talked about evaporation here in the open liner, so same thing happens in the double ring liner also. So it's preferable to seal them. That way we have less you see the less area to have the contact with the environment, or to have evaporation effect. Okay, so the advantage of these type of infiltrometers are they can permeate large volume of soil, because we're putting that in the soil directly, right? And there are two forms, as you saw. One is the open, the other is sealed one. So these two are like sealed one. That way we're sealing the majority portion of that. Still we have to keep it open like a piezometer, just to maintain the atmospheric pressure, right? And the open rings are less desirable because mostly it is because of the evaporation. For example, if the hydraulic conductivity is 10 to -7 centimeter per second, it is hard to separate a drop of 0.002 inches per day from the evaporation, right? And then if any evaporation you're getting, so how do you separate whether the drop in water level was from the percolation or infiltration, or from the evaporation? For that reason, the sealed are always preferable. So you want to see the picture of that, you see, it's like that. We maintain the water, flow of water here, you see. We fill outside with water, we fill inside with water, right? And we have two ways, and then we measure the volume of water going to maintain the same head, or sometimes what happens is we just simply measure the height of the water inside, right? These are the sealed one, okay? And these are the double liner type of, you see, you have outside circular double liner, you have rectangular double liner type of infiltrometers. Okay, so single ring or double ring. Single ring is less favorable because it allows lateral flow beneath the ring, as I told you before, and it is susceptible to temperature variation. But if you have double ring, then the one you have inside is less susceptible to temperature variation because the outer ring is protecting it. Okay, so sealed double rings, because of all those advantages, are the most successful and most preferable, although they are more expensive, and the most, I would say most expensive. The common is 12 foot by 12 foot outer ring, and 5 foot diameter inner ring is the most common one. So this is a schematic of the infiltrometers. Like you have a soil, this is the soil you have, and we put bentonite grout just to make sure that the flow is vertical down, one dimensional, right? And on top of that we put the loose sand in it. Okay, so this is the wetting front of the liner. This is okay, so this is the wetting front of the liner from where we're supplying water in. So water keeps on percolating down from the liner, right? So as it moves down, the wetting front means the separation between the saturated and the unsaturated. So other words, wetting front is the front of the seepage water. Okay, that's the wetting front. So we put sand in there. That is a filter layer that will help to level the things out, right? And then that'll help in the transition process, right? And we put all those rings sealed in bentonite. That way the side is not affecting that much, right? And then we put a plexiglass lid on top of that. That way we're covering it, okay? And then we supply water from the reservoir, right? And we also have the graduated cylinder. So depending on what we're expecting, right? So the beauty of graduation cylinder is you know the head difference, and you can record the amount of water going inside, percolating down. In that, when you supply from outside all the way to the top using the graduated cylinder, and then stop the valve, then let the water percolate down and record the head difference, the height of the water going down with time, exactly in the same way we do in the falling head permeability test. That way you can get the hydraulic conductivity. Okay, sometimes in double ring infiltrometer we use the float system. Okay, this is like you have a clay liner and you put tensiometers. The objective of putting tensiometer, twofold objective. One, we can measure the moisture content of the soil. At the same time, we can measure the suction in the soil. So higher the degree of saturation, lower the suction. Okay, so just to double check what's going on, we put the tensiometers. Okay, and then we put the flexible bag, and the sealing phenomena is exactly same as what you saw in the single ring one, right? And we seal them completely as we did before, and then we let the water go in, right? And then the tensiometers will tell you if the water is hitting the tensiometer, that means no suction in there. That means the suction value is 0, and you can record 0 suction in the tensiometer. 0 suction means 0 negative for water pressure. Okay, so rate of infiltration is in these type of infiltrometers are measured by small flexible bag like that. The bag is gradually depressed, right, in the liner as the water moves down, and the outer ring forces the infiltration from the inner ring to be more or less one-dimensional, because that's the objective of the outer ring. And the covering the inner ring with water mostly insulates it substantially from the temperature change. Okay, so this is the objective. So I mean, we talked about that. And the bag you have in this double ring infiltrometer, seal infiltrometer, that serves to stabilize the pressure between the inner and the outer rings. Otherwise there will be flow. Okay, so if there is a pressure difference between inner and outer, there is a possibility that flow from the outer will flow into the inner, or vice versa. Okay, so the other one, very expensive but very accurate one, is called lesimeter. Okay, so what we do in lesimeter is, even though the water level in the, but this is lesimeter, we'll talk about that when time comes, but even though the water level in the outer ring fluctuates, the differential pressure between the inner and outer ring is always 0, because the bag, pressure bag, is controlling everything. Okay, the test pad is usually for 40 foot by 50 foot by 2 foot, or 40 foot by 50 foot by 3 foot, depending on what we are using. And the total cost of a test ranges about $10,000. It takes about 1 to 2 months, because these are field tests. Okay, and the other device that we use in the field tests are called lesimeters. Okay, so what we do is we leave some pipes and some type of devices from where we can collect the leachate. So when we do construction of the construction of these clay liners, we leave some pipes in. That way we can collect the leachate water as it gets at least out from the liner system. Okay. Then what we do, we measure the water comes out from the bottom of the liner. As the pressure increases, as the water flows, as the water penetrates, right? So it is a direct measurement. Okay, so if we are talking about the field test, sometimes even you can do that in the real landfill, or you can do that for the field situation also, where you are making test pad. And when you are making test pad, you put all those pipes in when you are compacting for the test pad, and then supply water from outside and see how much amount of water is actually leaking through. So it's a direct measurement, and it is the most accurate one. So, but it takes a long time for the water to flow down from here, because the hydraulic conductivity of the liner is pretty low. Right, and it need to be put during the construction. Okay, so even for the test pad during the construction, if you're talking about the real flow of leachate, then we may want to put that during construction in the new sites. Okay, so the limitation of the field test, the field tests still have limitation. So the concept of field test, you have D is the head of water, D plus EL of the soil will give you the hydraulic head difference, right? And then because it's the front of the wetting front, you see, There's a sealed soil and there's soaked soil where water moved up to this point. So the exit of the water is this point. That way your head difference is D plus L1, right? And then the water flowing from top to the bottom, that is at the length of L1, so hydraulic gradient is D plus L1 over L1. That's hydraulic gradient. So everything is measured based on the principle of Darcy's flow. Okay, and hydraulic gradient is important. So limitation of the field tests are, first, we measure the infiltration rate. It measures the infiltration rate instead of the direct K value. Okay, in lab tests we directly measure the hydraulic conductivity, right? And here we indirectly calculate hydraulic conductivity based on the infiltration rate. Okay, for that reason we need to get the hydraulic gradient first, because it varies with the travel of the wetting front. Okay, and hydraulic conductivity is D plus L over L that we talked before, that assume the pressure head at the wet front equal to 0. Somewhere here, pressure head here is 0, right? And the okay, so when it comes to that point, it keeps on changing. Okay, so for that reason, it is this assumption is a little conservative, because what we assume is, let's say, if we talk about the soil liner all the way here, right, then the hydraulic gradient is high and the length is high too. For that reason, it will give us, this assumption will give us little. In reality, D plus Li, hydraulic gradient is D plus Li over Li. When we make our calculation, what we do is, if L is the length of the thickness of the clay liner, our calculation tells us, okay, the hydraulic gradient is D plus L over L. Okay, so mainly that gives us conservative value. Field hydraulic test will give us, K test gives us conservative value. That's mainly because the metric potential, mostly what happens is when the water is flowing down, right? So here at the wetting front, what we are assuming is hydraulic conductivity is, but let's say the water is in the atmospheric pressure, right? But below that, because it is not completely saturated, it has negative pore water pressure. That is called suction. So negative pore water pressure increase effective stress. Okay, because of the suction, it sucks the water quickly compared to the because of that suction, that metric potential is also called suction. The actual hydraulic conductivity should be larger, because the difference between the hydraulic conductivity is pressure head difference, right? So because you have negative head difference, then actual hydraulic conductivity with the suction will be the difference in pressure from this point to this point, where this point we're assuming that is zero pressure, but in reality it is not zero pressure. At this point it has negative pressure. So actual hydraulic conductivity will depends on what amount of suction you are getting here. Okay, so if we talk about, let's say, and because of that, you see, because of effective stress, so higher the effective stress, that means higher the difference in pressure from top to the bottom, right? And the higher the effective stress, the lower the hydraulic conductivity, because lower the pressure we are getting, higher the overburden stress that we get, right? Then higher the consolidation or compaction in the soil sample, right? That'll reduce the hydraulic the void ratio. Lower the void ratio, lower the hydraulic conductivity. So overburden stress is essentially 0, right? I mean, in fact, it's hard to study the effect of stress in the field. Okay, so for that reason, the use of the lab data to adjust the field data. So in that situation, we assume that they have the sham trend. So what we do is, in the field, there is no overburden pressure, because we are running all those tests before we dump the garbage on top of that, before we complete the, let's say, before we complete the sale, landfill sale, right? For that reason, you cannot increase the overburden pressure. You can see the effect of overburden pressure to reduce the void ratio and to reduce the hydraulic conductivity in the lab, right? In the field, what we can do is we can also increase the overburden pressure by increasing the pressure in that soil sample itself, right? So we can consolidate that at different overburden pressure, and we can run the hydraulic conductivity test on that. Okay, so for that reason, higher the effective stress, lower the hydraulic conductivity we get. So what we do is we run the lab test and get the relationship between effective vertical stress and the hydraulic conductivity for that soil, and then make a chart. And from in the field, our effective overburden pressure is almost nothing, right? And then what we do is we make a parallel curve from here to check what will be the impact of the overburden pressure that we get in the future from the garbage and the topsoil, all those things, and how much reduction in hydraulic conductivity we get in future. We can estimate that. So always lab test and field tests are in lab test plus field test in combination with them to design the landfill liner system is always preferable. Okay, so so what we typically do is at the hydraulic during the hydraulic conductivity test, so most of the test is terminated when the hydraulic conductivity drops below 10 to -7 centimeter per second. So what we do is we keep on running the test, right? And we record the time required to drop the hydraulic conductivity to less than 10 to -7 centimeter per second. Generally what happens is, time increases, hydraulic conductivity decreases anyway. Okay, for that it takes about 2 to 8 weeks, right? Time increases, hydraulic conductivity increases because the sample gets saturated, soil gets saturated, right? So if the hydraulic conductivity we're getting at certain time is 10 to -7 centimeter per second, then we stop there. So it takes about 2 to 8 weeks, right? If after but 2 months, if we cannot get our required hydraulic conductivity, okay, then the liner doesn't work. So we have to keep that in mind. Okay, so hydraulic conductivity is less in the beginning. Okay, this is called this is the way how we do the field tests. With time, hydraulic conductivity decreases, right? And then we keep on testing them. So the difference between field and the lab test is this. It's preferable to do both tests. One reason for that is you want to see the effect of overburden pressure, right? And the labs are less expensive than the field test. And you can do all types of scenarios in the lab. You cannot do that in the field. Okay, so you can do much more samples in the lab. Even though you screw up the result test for one sample, we can repeat the test in other sample, right? So we can simulate certain conditions like back pressure to get rid of the ear void or complete saturation, or overburden pressure, because false saturation situation is bad, because if the soil has a degree of saturation less than 100%, that'll give you lower hydraulic conductivity. That is disastrous. Okay. So, so we can also simulate the overburden stress. We can also use the actual, similar actual waste in the lab, right? That is, we don't have that much flexibility in the field. So if the liner is free of defects, then the lab field hydraulic conductivity should be same in reality. Then if not, then the way how we compact it, how we prepare the sample in the lab might be different than the way how we compact the sample in the field. Okay, so more possibility to have error in compaction and preparation of the sample in the field is more possibility to have those errors than in the lab, because lab we are compacting, we are controlling the compaction situation and testing situation. So field error might be bad, it might be more. So there is a possibility we may end up getting higher hydraulic conductivity in the field than in the lab, which is disastrous, which is not good. Okay, so now we are done with hydraulic conductivity. We talked a little bit about compaction. It's good for you to take a 5-minute break and then or maybe 10, depending on what you want to do, and come back and watch the video again. So now let's talk about compaction. So what happens in compaction is, as I talked before, we apply energy in the loose soil, and because the energy or the impact energy we are using, or any sort of energy we are using with water, then we are moving the particles from one place to the other to fill the void space. So mostly this smaller size particle can easily move to fill the void spaces. Even big size particle can move depending on how big the voids are. Water helps to lubricate and move them. Okay, so compaction, soil is in geotechnical engineering or civil engineering design or civil engineering projects, soils are compacted to improve the shear strength, because compaction will increase the density, that will increase the shear strength. All right, to reduce the compressibility, because when we compact, we move the particle from one place to the other. We already changed the volume of the soil. That way, further increase in stress will reduce the compressibility or settlement. Okay, and we also reduce the permeability. I mean, it is important for us in compacted clay liner to reduce the permeability. Okay, because the void space reduces, the hydraulic conductivity reduces, and the permeability reduces. Void space reduces, the void ratio reduces, the density increases, and the permeability reduces. Okay, and it is also because we reduce the void space, the chances of the water to go inside and fill the voids the volume of the water going inside and filling the void space is less. That will reduce the shrink and soil potential of the soil. And it also reduces the liquefaction potential, because mostly liquefaction occurs in loose sand. It is not important for, it is important at one point, but not that critical at this point. But mostly liquefaction occurs in loose sand. So when you have earthquake load coming, that earthquake load pushes the saturated sand and push water. Water will provide upward pressure, that is called the pore water pressure, and that will reduce the effective stress and convert the soil into fluid. Okay, so that type of phenomena in terms of behavior, right? And that is the phenomena is called liquefaction. So the only way we can reduce the liquefaction by converting loose sand into dense sand. The only way you can do it by compaction. One way, not the only way, one way to compaction. And it also reduces compression due to weighting, because when you weight this sample, then what happens is, because of that hydraulic weighting, there is a compaction going on. Okay, so but when you have the already compacted sample, that extra compression are not getting due to weighting. Okay, so that's important. And it also reduces the space where you have chemical reaction going on, because void ratio reduces, it reduces the chemical reaction in the system. Right? So behavior of the soil during and after the compaction depends on the type of soil, whether it is a fine grained soil versus coarse grained soil. So behavior you need for the compacted clay liner is different than the behavior you need for the drainage layer or filter layer. Okay, so it also depends, the behavior of the soil during compaction also depends on the compaction moisture content. We'll talk about that in detail. And it also depends on method of compaction. As I told you, if we are doing kneading compaction, the behavior is different than when we do the static compaction. Okay, it also depends on whatever equipment we are using. Okay, so the goal for us for the compaction in any construction project is is mainly and even for the building construction is different than the goal for the compaction in the landfill liner. Okay, so in building construction, we want to increase the density, we want to increase the shear strength, we want to reduce the compressibility. Okay, for liner, our we are trying to reduce the void ratio to reduce the hydraulic conductivity. We have to keep that in mind. Okay, because we're not too much concerned with the bearing capacity of the liner. Okay, so compaction in clay liner is mainly to reduce the hydraulic conductivity. Okay, so that the high permeable zone may not be of great concern for which may not be a great concern for the building construction, because higher the permeability, higher the pore water pressure reduction quickly, and the better, in fact, for the building, right? But lower permeability is much better in the landfill liner. So that's a big difference. Okay, so the compaction, there are different variables for compaction. So one thing that controls the compaction characteristics is the soil water content, or I may end up saying WC from now onwards, and type of compaction you are doing. Okay, whether you are doing kneading compaction versus static compaction. The compaction effort or behavior of the soil depends on compaction effort also. More energy, more compaction, more different behavior compared to the less energy. And size of the clod. Bigger the size of the clod, for the same amount of energy, maybe the hydraulic conductivity might be different than for the smaller clod size. Okay, clod size means, you know, when you add water in clays, the clay become separate into clods, like the mound type of thing. Mound is big scale, clod is small scale. Okay, and it also depends the bonding between different lips, because in real practice, if you're making 3 or 4 foot thick clay liner, you are not putting all 3, 4 or 4 foot thick clay there. We put clay in every 6 or 9 inch lift, and then we spread the clay, spread water in there, and then we compact, right? And the bonding between the previous layer and the new layer depends on how percussion you are applying, how much percussion you are applying. So if that bonding is weak and there is a crack in between, then there's a possibility that those places will create non-homogeneous or the heterogeneous hydraulic conductivity in the soil, and that may be bad. Okay, if it is continuous, then that might be the source of leakage. It's important. So it also depends on compaction equipment. So kneading action versus the static pressure action depends on what type of compaction equipment you are using. We'll talk about that. And it also depends on how much effort we're putting for the desiccation prevention. Because as I told you, desiccation is disastrous. That will make the soil cracking, and then those cracks are the sources of high permeability zone. Okay, it is extremely important. So the laboratory compaction test is done in the lab using the Proctor compaction device. Okay, so let's deal with that. So this is a Proctor compaction device. Okay, so what we do is we have a Proctor compaction device that is about slightly more than 4 inch diameter and 6 inch tall. And then we put the mold. You see, this is a mold, and then we have a lid on top of that, just to help the compaction process, right? And this is a hammer, so you can pull this guy up and drop it. So the length of the rod, you see, you can put this piston up. This is a piston, so you can put this hammer up. This hammer itself is like a piston, so you can put this thing up, pull up and drop it from the height of 1 foot or 1.5 foot, depending on what type of compaction test we are doing, how much amount of energy we're putting, right? And this lid is also called collar, so we use that for extension purpose only. So what we do is, this hammer, let's say this hammer is 5.5 pound weight, right? When we drop, we put the soil up to 1/3 layer, or depending on what type of compaction you're doing. Let's say we take the soil from the side and then prepare it and put 1/3 of this height, this height of the mold itself with soil, and then we drop this hammer. We lift the hammer, drop by 1 foot, and the height of the weight of the hammer is 5.5 foot. So we drop 5.5 pounds. We drop continuously. We keep on rotating while we are dropping, and we count the number of drops. So we drop the hammer for 25 number of blows, and then we add more soil on top of that, up to, let's say, pretty close to 80% height, right? And then we drop the hammer again 25 number of times. Okay, now the volume reduces, and then we add more soil on top of that, let's say up to, and then we add this extension here, and then after we add that extension, we fill up to the half of the extension, and we drop the hammer again for 25 number of blows, and we rotate the hammer while we are dropping. Okay, that way we are uniformly compacting the soil inside, right? After that, now we have total 75 number of blows, 5.5 pound and 1 foot high. That way you can easily calculate energy. Energy is work done by work done. So work is force multiplied by the distance it travels. So that force dropped by the distance of 1 foot, 5.5 pound force dropped by the distance of 1 foot for 75 number of blows, 25 multiplied by 3. Okay, so that will cause the inertia. That will give you the total inertia that you are putting into the soil specimen. Okay, that depends on whatever compaction we are doing. And after you are done, we just take using the frost red knife, you just floss the surface of the soil, and then now you know the volume of inside volume of this container is 1/30 cubic foot. Okay, now you know the volume. Then take the weight of the mold before you put the mold, put soil in it. Right, and now after you have the soil, compacted soil in it, bring that into the scale and get the weight again. So that'll give you the total weight of the soil you have inside. If you subtract from the original, you can get the total weight of the soil you have inside the mold. So now the weight of the soil, if you divide that weight with the volume of the soil, that is 1/30 cubic foot, then that'll give you the bulk density, bulk unit weight of the soil. Okay, now you got the bulk unit weight. You know what amount of water you are using to mix the soil. You may not know that, but you mix certain amount of water in that and then mix the soil. So put this soil, take the soil from top, middle and bottom and put that into the oven and get the moisture content in the following day. So now you know the moisture content, you know the bulk density, and divide the bulk density with 1 plus moisture content in fraction. That'll give the dry unit weight. Okay, so that way from bulk to dry you can get. So you know the moisture content and corresponding dry unit weight for that total 75 number of blows of the 5.5 pound hammer dropped from 1 foot. Okay, and then add more water in and take the soil from the same batch, not same soil but same stack, add more water into it, right, and compact with the same amount of inertia. Now your dry unit weight increases. Keep on adding more water and do the third test and get the maximum dry density you are getting, right? And then dry density increases, right? And then keep on doing that for 4 or 5 different times. Okay, so but there are 2 different tests we do. One is standard Proctor test, that is simulated for certain type of field compactor we have, and the modified Proctor compaction gives you a little more inertia, that is equivalent to the state of the art or maybe the compactor we use nowadays, right? So so the volume, the same mold for both tests, 1/30 cubic foot. And standard Proctor, as I told you, we put the soil in 3 layers, but in modified Proctor, to put more inertia, which is equivalent to more inertia we are putting in the field, if we do, right, that will compact the soil in 5 layers as opposed to 3 layers. And number of blows we are using in both are same, 25. And the hammer we are using for modified Proctor is 10 pound as opposed to 5.5 pound for a standard Proctor. And the drop height in modified is 18 inches as opposed to 12 inches in the standard Proctor. And that gives you, if you multiply all those things, right, 5.5 pound, 12 inches, 25 blows multiplied by 3 over 1/30 cubic foot, that'll give you the input inertia of 12,400 pound-foot per cubic foot of volume. Right? For the same volume, modified will give you almost 4 times, even more than 4 times higher inertia. That means you get more times, more dry density for the same moisture content, dye into it for the same moisture content compared to the standard Proctor. Okay, what type of inertia you are putting in the field depends on what type of equipment you are using. You can correlate that inertia with the lab compaction test. These are lab compaction tests. Okay, so sometimes we also use for landfill sites, we also use the reduced Proctor. Okay, so reduced Proctor is exactly the same as standard Proctor. We use the same Proctor compaction device, but what we do is, in place of 25 number of blows, we use only 15 number of blows per layer. So that'll give you less inertia. Okay, so that way we can compare. Okay, the inertia, as I told you, the inertia we're getting is 1 foot multiplied by 5.5 pound multiplied by 25 number of blows multiplied by 3 layers, everything divided by 1/30. That is the inertia you're getting. Okay, so mostly we compact the soil with required compaction effort, whether it is a reduced compaction or modified or standard compaction, and then measure the weight of the moist soil mass, as I mentioned you, and then measure the volume of the soil mass, which is typically 1/30 cubic foot for the standard device, and take the representative soil from the top, bottom and middle and put that into the oven to get the moisture content, and add more water into the soil. Take the new soil, as I mentioned you, add more water and repeat the process again. Typically we do 4 or 5 tests. I don't worry about 4 or 5, and I may end up going, my students go even 6 or 7, because their first assumes moisture content is so low that the dry density doesn't go down. So I prefer everyone to have at least 3 points after you get the maximum dry density. So doing more tests is always good. Okay, so what you know is unit weight is total weight of the soil you have in that compacted soil over the volume, that is 1/30. Okay, and then as I told you, moisture content is the moisture weight of water that you get, that is that you evaporated after putting in the oven for 24 hours, over weight of the dry soil multiplied by 100 will give you the moisture content. And then dry unit weight is bulk unit weight that you got from the compacted soil divided by 1 plus moisture content in fraction. Don't put in percentage. Okay, so that'll give you dry unit weight. Now, so if you recall soil mechanics, the soil has air void, water void, and soil solid. The objective of compaction is to reduce the air void, not to reduce the water void. Okay, to reduce the water void we use consolidation. Okay, so we reduce the air void, so that means the soil has same weight, but because the air void is reduced by compaction effort, volume decreases. So for the same weight, volume decreases, increase the density. That's the objective. Okay, so if you, let's say, if you put enormous energy, let's say if you are compacting the soil for weeks, months, maybe a year, keep on compacting that. So slowly, with increase in compaction effort, the amount of air void that you are diminishing keeps on increasing. In other words, amount of air void reduces with the increase in compaction effort. Okay, so it keeps on the air void keeps on diminishing or lowering in volume. Okay, and there is a point where all air voids are gone with your compaction efforts. Okay, after that, if you try to compact, the soil is completely saturated, water is incompressible for soil mechanics, and then you cannot, because at the bottom you have a opaque or impermeable layer, you cannot drain the water out. For that reason, it is impossible for you to compact beyond that. Okay, so this situation where you are using enormous or amount of energy to get rid of all air void is called zero air void situation. Keep that in mind. Okay, so that means when you apply enormous energy, you get to this situation in real, standard, modified, whatever type of compaction you are doing in the field, you are not coming to this level. So this is the maximum possible density that you get. This tells you maximum possible bulk or dry density that you get with enormous amount of energy. So our lab compaction effort should give you the dry density much lower than that. So what is that dry density that you can maximum achieve by enormous compaction effort? You can easily calculate doing that. You see, at zero air void situation, right? If you recall soil mechanics, gamma d, that is dry density, is equal to G sub S, that is specific gravity of the soil, multiplied by gamma W, that is 62.4 pound per cubic over 1 plus void ratio. Okay, now you are reducing the void space by compacting them, right? Because air void is diminished. At that situation, you see, the soil is completely saturated, and the equation you have is G sub S W, that is equal to S E. S is degree of saturation multiplied by void ratio is equal to specific gravity multiplied by moisture content in the soil. Because in this situation, no zero air void situation means the soil is completely saturated. All void space is filled with water. That means S is 1. Right? The corresponding void ratio in that situation will be G sub S, specific gravity, multiplied by moisture content. For example, if you started your test in a clay that has G sub S of 2.7, okay, that you get from the lab test, so 2.7, and then you are running your first test with moisture content of 2%, then your W will be 2 over 100. So, okay, 2.7 multiplied by 2 over 100 will give you the corresponding void ratio in case you are applying enormous amount of energy to compact it to get rid of all air voids. right? Now you can substitute that E here. So 2.7 multiplied by 62.4 over 1 plus whatever you get from here will give you the maximum possible dry density from that moisture content. Okay, so that way you can get the dry density for in case there is no air void in it. Okay, in case you are putting enormous inertia. So that 0 air void dry density for that particular moisture content should be less than the should be more than the dry density that you are getting, dry unit weight that you are getting. I interchange unit weight and density, just don't be confused. I mean, mostly gamma is unit weight, rho is density. Okay, so that dry unit weight should be less than the dry unit weight for 0 air void situation. So for 0 air void dry density calculation, what you need is you just need specific gravity of the soil and the corresponding moisture content. Okay, so now your 0 air void dry density is equal to GS gamma W over 1 plus GSW, where G sub S is known, 2.7 for clay, 2.65 for sand, or it is given gamma W is 62.4 pound per cubic foot, and moisture content, you are calculating the maximum 0 air void dry density for certain amount of moisture content. That gave you the dry density in the lab. Okay, so this is the way how we get the numbers. What we do is, let's say I put 11% moisture content in that soil and compact it, and at the end of the compaction effort, I got the dry density of the soil to be, let's say, 94.3 pound per cubic foot or something. Okay, and then if I put that 11%, no, it's not 11, it's 10.5%, right? So if I put 10.5% in the value of W here, you see, 10.5%, let's say if gravity is 2.65 or something, then I can easily calculate what will be the corresponding value of 0 air void gamma D for that soil. So for that, by putting all those numbers into that 0 air void gamma D equation, I got the gamma D for that soil. If there is no air void, if I compact it hard, I can bring it up to, let's say, 129.8 pound per cubic foot or something like that. Right, and then I take the soil sample and I add more moisture in it. Let's say I run the Proctor compaction test for 14% moisture content, and I got the gamma D value from that compaction effort to be, let's say, 98%, 98 pound per cubic foot. Right, if I substitute that W with 0.14, I get 0 air void gamma D equal to, let's say, 121 pound per cubic foot. It decreases, because when W increases, gamma D decreases, right? Because W is the denominator. Okay, then I increase the amount of water in the soil, take the new batch, increase the amount of water, and compact it. Now I got 121, let's say 100.5 pound per cubic foot, and the corresponding 0 air void gamma D for that is this, right? And then I add more water. Now my gamma D decreased to, let's say, 99. That means now I'm getting maximum dry density in between somewhere, right? And then I want to go further 1 or 2 points because I want to make sure. Then I get the new sample, add about 26% water in that, compact it. I got gamma D equal to about 93 pound per cubic foot. Corresponding 0 air void gamma D for that is this. You see, now degree of saturation is increasing. For that reason, this line is getting closer to this one. At one point, if you have enormous moisture content, if you have a moisture content that completely saturates the soil, this will close with this one. So at degree of saturation 100%, those two lines will close, but at that point you cannot compact the soil. So it is impossible for this line to toss this one during our Proctor compaction effort, although theoretically it's possible. Okay, now I make a smooth line here. The only reason we want to make 0 air void line is that's the maximum point that you can get. Okay, and then we connect those blue dots, blue diamonds with a smooth line, and then that'll give me the maximum possible dry density. Here is this point. Okay, this is the point where we didn't even test. Okay, so that is about 10.5 pound per cubic foot, and the corresponding moisture content is called optimum moisture content, that is 20%. At moisture content 20%, we get maximum dry unit weight. Okay, so this is the way how we plot the data, represent the soil test data to give maximum dry density and optimum moisture content of the soil. Okay, this is called 0-year void line, and this is called Proctor compaction curve, where W of 20% is optimum moisture content for this soil, and gamma D of let's say 102 pound per cubic foot is the maximum dry density of this particular soil. Okay, this is the way how we represent the lab test samples. Okay, compaction of the fine grained soil is done. You see, if you see different compaction effort. Okay, so higher the compaction effort, the higher the dry density, and lower the optimum moisture content. Keep that in mind. Okay, so like modified Proctor, you use more energy, you get. Let's go with the reduced Proctor. That is 15 number of blows. Less energy, you get maximum dry density of this much value with this moisture content. Right? If you increase the compaction effort to standard Proctor, you increase the maximum dry density, reduce the optimum moisture content. If you increase the modified Proctor to modified Proctor energy, you increase the maximum dry density, reduce the optimum moisture content. Okay, so there is a possibility that in the field, so whatever amount of energy you are using in the field, that should simulate with the lab. That's one thing, but it's not always good to have more energy, because there is a relationship between the moisture content and the hydraulic conductivity. Okay, for us, more important is hydraulic conductivity as opposed to the strength increase. Okay, we'll go into detail on that. Okay, so higher the compaction effort, higher the maximum dry density or dry unit weight, and lower the optimum moisture content. Keep that in mind. Okay, so in the field, in the lab, what we do is, let's say we took the middle line, standard Proctor. So we give them, in the previous example, the maximum dry density is 102 pound per cubic foot, right? The optimum moisture content was 20%. Okay, then what we tell in the field is, okay, the field density, there's one way of writing specification is, we say, okay, we don't care, after you complete the compaction effort, we come there and we measure the density, dry density or dry unit weight of the compacted field. Okay, if that dry density should have more than 95% relative compaction. That is, the meaning of the relative compaction is gamma D field gamma D, field dry density unit weight in the field over dry unit weight, maximum dry unit weight you got from the laboratory test for that standard or modified depending on whatever compaction effort you are using. So I need 95% relative compaction, means in that example you have, in the previous example, you have 102 pound per cubic foot of maximum dry density. So in the field, if the dry density in the field is less than 0.95 times 102 pound per cubic foot, then we don't accept that. Then they need to apply more compaction energy or do something to increase the dry density or dry unit weight to the required level. Okay, so relative compaction is different than relative density. Relative compaction is field dry density of the compacted field over maximum dry density or unit weight. It is synonymous, because density, if you multiply density with the gravity, that will give you unit weight, right? So field unit weight divided by maximum field dry unit weight over maximum dry unit weight of that particular soil in the lab. Okay, and typically the relative compaction in the field to be accepted should be more than 90, depending on the situation. Some projects consider 90%, some projects consider 95%. So depending on the specification. Okay, so let's do one example. So you have soil sample that you collected. First, you mix the soil sample with 6.2% water and applied compaction effort, and then after, let's say, standard compaction effort, and your bulk density, bulk unit weight you are getting after that, let's say 75 number of blows, that after third layer is 16.9 kilonewton per meter cube, right? And then you took new batch and you added 8.1% moisture in it, and you got bulk unit weight of 18.7 pound per cubic kilonewton per meter cube, and then you added 9.8% moisture, third batch, more moisture, and then compacted, you got higher bulk unit weight, that is 9.5. Bulk is right after compaction, okay, 9.5 pound per kilonewton per meter cube. Then you added more water and then you further got the bulk unit weight higher, 20.05. Then you added 12.3% moisture, more moisture, you got bulk unit weight of 20.4%, 20.4 kilonewton per meter cube. And then further you added moisture, and you see it is increasing, right? Then you added 13.2% moisture. Now your bulk unit weight decreased to 20.1. This is not the perfect example. I want to go 2 points beyond the maximum dry density point, bulk density point. Okay, so all these things you can do while you are compacting. You can estimate them. Okay, now please calculate the dry unit weight, and then dry unit weight and water content at 95% standard Proctor compaction. Please calculate that. Okay, that's your job. And I'll do one example, and also calculate the degree of saturation at the maximum dry density level. Okay, so what is given to us is also calculate calculate and plot the zero-year void line. So specific gravity of that soil is 2.7. Now you have everything that to start with. You see, you have now make an Excel spreadsheet or table where first put moisture content 6.2, right, and gamma is 16.9. If you recall the equation I gave you, the gamma D, dry unit weight, is bulk unit weight divided by 1 plus W. So 16.9 over 1 plus 0.062 or 1 plus 6.2 over 100 will give me 15.79. Right, and zero-year void line is same moisture content, specific gravity is given. So if you plug in the equation, the W is equal to 0.062 or 6.2 over 100, and G sub S is equal to 2.7. That will give you gamma D zero-year void will be 22.7. So if you go into detail on that, I didn't bring that equation here. You see, so like that. So 2.7 multiplied by 9.81 kilonewton per meter cube. Gamma W is either 62.4 pound per cubic foot or 9.81 kilonewton per meter cube over 1 plus 2.7 multiplied by 6.2 over 100 will give you 22.7 kilonewton per meter cube, right? Do the same thing for 8.1 moisture content. So 18.7 over 1 plus 8.1 over 100 will give me 17.3, and exactly in the same way you get gamma D for zero-year void lines. That way you complete all those things. So what you have now is moisture content, dried unit weight, and the dry unit weight in case there is no year void in it or zero-year void situation. So if I plot those three things in a chart, right, x-axis is moisture content, y-axis is dry unit weight, I get these type of curves, and it is not perfect, but it's going up and up and up, and it went to the highest here, maximum point, and then it dropped down. So this is the zero-year void line. So good news is this is not touching this. Okay, so now my maximum dry density, the optimum moisture content for that soil is the moisture content that gave me maximum dry density, that is 12.3%. And there is a possibility that maximum dry density you can get in a point which is not even tested one. Keep that in mind. You have to make a smooth line. Okay, and the maximum dry density for this soil, gamma D max, is 18.22 kilonewton per meter cube. I just scaled out from the y-axis. Okay, and this is the zero-year void line. Okay. Another example, you have moisture content 3, 6, 9, 12, 15, and 18%, and the corresponding bulk unit weights are 16, 18.5, 20, 19.5, 18.2, 16.8 pound per cubic, the kilonewton per meter cube. So what I forgot here is now your 95% relative density that you require in the field will be 18.22 multiplied by 0.95. Okay, in your question you have you see, degree of you did dry unit weight and water content at 95% standard compaction, right? So calculate whatever amount I got, multiply that with 0.95, right? And you can also calculate degree of saturation for at maximum dry density. So gamma D is equal to GS gamma W over 1 plus E. Okay, so gamma D is known now at maximum dry density. G sub S is 2.7. Gamma W is 62.4 over 1 plus E. That is void ratio. Now you got the void ratio from there, right? S sub E is equal to W multiplied by S multiplied by E is equal to W multiplied by G sub S. right? So degree of saturation, yes, multiplied by E that you got from the previous example from gamma D is equal to W, you see, G sub S is 2.7 multiplied by W, that is optimum moisture content that you got from the lab test. That way you get the the degree of saturation at the maximum dry density, right? And at 95% of the compaction level, you see what will be the dry density. So multiply that 18.22 with 0.95, you will get a point somewhere here, right? And then make a line from there that will give you the density that unit weight that you require, and that will cross your the Proctor compaction line into two different places here, right? So you can get that 95% dry unit weight at two different moisture contents. So that was the question. Okay, let's do another example. Maximum dry unit weight and optimum moisture content of the soil. Please calculate that. This is 2.7, right? And zone of, there's an error here. It's not zone of compliance, it's zone. Zone of compliance if the acceptance relative compaction in the field is 95%. So field unit weight should be at least 95% of the maximum dry density you got from the lab, and the field moisture content should be in between plus or minus 2% of the optimum moisture content. Okay, let's see this example here. So this is exactly the same. You see 16 over 1 plus 3 over 100 will give me 15.53, right? And whatever equation I showed you for 0-year void line, if you substitute those this moisture content and a specific gravity of 2.7, you can get 24.48. So this is pretty simple to calculate, right? After you get that, okay, then we plot this in the moisture content in x-axis and dry unit weight in the y-axis. So if you plot all of them, you can get this type of bell-shaped curve, and the maximum dry density here is 18.35 kilonewton per meter cube, and the optimum moisture content in this example is 9%. Now the question is, in the field, anything that gives you dry unit weight more than 95% of 18.35 is acceptable. So 95% of 18.35 is 17.43 kilonewton per meter cube. So make a line from 17.43 all the way horizontal line, that anything above that in the field is acceptable. If the field unit weight is less than that, not acceptable, right? So good. Then the other thing is, other condition is, if the field moisture content is in between plus or minus 2% of lab moisture content, that means plus or minus 2%, that means optimum moisture in optimum moisture content, right? So optimum moisture content is 9%, so 9% minus 2% is 7%, 9% plus 2% is 11%. So if the field moisture content gives you is more than 7% and less than 11%, that is acceptable. Okay, so we need to control that also. You cannot put a lot of water, you cannot put less water, all those things. So these are the conditions you have. So the dry unit weight should be more than 7.45. So anything above this horizontal line, 17.43 is acceptable. So anything in between 7% moisture content and 11% is acceptable. So this hash zone is the zone of compliance. If the field compaction dry unit weight and the field moisture content is plotted in between this line, acceptable. But it cannot go beyond 0-year void line, because anything goes beyond 0-year void line means you are not simply compacting, it's completely saturated sample, it's impossible zone. Okay, so this hash zone here is called zone of compliance. Okay, again, if the field data plots in between that, it is acceptable, otherwise no. There's more examples. You have soil sample from the above mentioned stack. Any stack was used to compact a compacted clay liner. Okay, so the specific gravity of the soil is 2.65. Modified compaction test was conducted at the lab that gave the following moisture content unit weight relationship. Then you can see here moisture content unit weight relationship, and you are assigned to inspect the compaction site. Okay, the specification tells that the soil should have at least 90% relative compaction for the moisture content within 0 to plus 4% of optimum moisture content. So either optimum moisture content up to plus 4%. If the optimum moisture content is 9%, so it up to 9 to 13% moisture content is acceptable. Okay, your job is to calculate the maximum dry unit weight and optimum moisture content by plotting the Proctor compaction curve. So and forget about this above mentioned stack. Okay, just replace this above mentioned stack with the one stack of soil, something like that. It's totally new example. Okay, and also plot the zero air void line in the Proctor compaction curve and show the zone of compliance. That is the acceptable zone in the curve if the field density and moisture or field unit weight and the moisture content is plotted within this zone. Okay, let's see. Here you have moisture content and bulk unit weight from the lab test. Okay, so exactly in the same way I got, using the equation I showed you before, I got for different moisture content different dry density and the possible zero air void dry density. Right, now I can plot them into this equation. Right, by plotting into this equation I got maximum dry unit weight is 19.1 kilonewton per meter cube, right, and the optimum moisture content was 10%. Okay, the field zone is the field dry density, dry unit weight should be at least 90% of 19.1, so that is 17.19. so I made a horizontal line from there, right, and the field moisture content can not be less than optimum moisture content and cannot be more than optimum moisture content plus 4%. So optimum is 10%. So the field moisture content cannot vary other than 10 to 14%. So I made a vertical line from 10%, I made a vertical line from 14%, and then I extended that all the way to the zero air void line, and then the hashed portion, if your field sample is plotted in between that, acceptable, otherwise no. Okay, in the exam or in your PE exam or in our exam here or in any calculation, you may end up given with the field bulk unit weight, field moisture content. So from the field bulk unit weight you can calculate the field dry density, dry unit weight, and you can plot the field dry unit weight and field moisture content based on that and see whether it lies within the zone of compliance or not. Okay, so we did that. Gamma D max and optimum moisture content. So field gamma D should be more than is gamma D. Okay, it's not gamma. Field gamma D should be more than 0.9 times 19.1, that is 17.19, and field moisture content should be 10 to 14%. Okay, so the behavior of a fine grained soil under compaction depends on different situations. Let's see that. You see, when you add, it's the exact same curve that I showed you before. I mean, it's schematically same, right? If you increase the molding moisture content, the compaction density or unit weight increases up to point B is the point where you have maximum dry unit weight, and corresponding moisture content is optimum moisture content. You see, when you see the soil fabric, here it is randomly oriented soil fabric, right? When it comes to point B, that is maximum dry density for lower compaction effort, the soil is still randomly oriented but little better than the point A. When it goes to point C, soil is starting to have parallel orientation. The plates are towards parallel orientation, but it's still a little random. That's okay. Now let's increase the compaction effort, compaction energy. As I told you, higher compaction energy increase the maximum dry density and lower the moisture content. Optimum moisture content. Now it has, because it is more energy, more close to each other, but still randomly oriented. But when it comes to the moisture content, which is equal to the moisture content that you got from the lower energy, you see, higher energy will convert all those randomly oriented particles into basically parallel oriented. So if the plates are parallel, the vertical hydraulic conductivity is much lower than the randomly oriented particles. So always, for that reason, we prefer to have more water in the landfill liner than the optimum moisture content, I mean up to 4% or something, as opposed to the drier side that we need for the building construction, those things. Because in building construction, drier side is also sometimes preferred because of the strength point of view, but we don't prefer that for the landfill liner. We always go for the wetter side of the optimum. Okay, this is the behavior. So if you want to see how different type of compaction effort gives you different the compaction curves, you can see, for example, number one you are seeing here is the laboratory static compaction. It's very static compaction that is compacted with 13.8 meganewton per meter square, and you get you see, with higher moisture content you get maximum dry unit weight, and then it drops down. Okay, so for that particular soil, your zero air void line is this line. So nothing can go beyond that line. Okay, and then second one you have here is you are using modified compaction effort. So with modified compaction effort, then you get this curve, modified compaction curve, gave you this maximum dry density and corresponding moisture content, optimum moisture content is about 14% or something like that. Okay, and the third, number 3 here is standard Proctor. So first one is static compaction. Okay, the third one is standard Proctor will give you this. So maximum dry density with standard Proctor was about, let's say, 16.6 kilonewton per meter cube at the moisture content about 17.5%, something like that. Okay, and then the fourth is the laboratory static compaction test, but not with 10 times less energy than 13.8 meganewton per meter square. Okay, less energy. So number 4. So with 10 times less energy, we got the number 4 curve here, right? Which gives where you can see the increase in the dry density with an increase in moisture content. Okay, and the fifth one is field compaction. Okay, and when they were compacting that soil with rubber tired roller, that we'll talk about that rubber tire roller in the future, then what they got is they got the fifth line. This is the fifth line is this one. Okay, then they got the maximum dry density slightly higher than the dry density that we got from the static compaction test at higher moisture content with 6 passes, right? And when they use the same soil but compacted with shift foot roller, the same number of passes, right? Then what they got was number 6. Number 6 is this. They got this maximum dry density and the corresponding moisture content from that. So this is just for comparison. Okay, so for that reason, you see the effort that the rollers were using were pretty close to the standard Proctor compaction results. Okay, so in the field, we compact the soil with using different equipments, right? So it could be a sheep foot roller, it should be the smooth wheel roller, it should be a tamper or anything else, right? So it should be a pad foot roller or it should be grid foot roller, anything, right? We'll talk about that. So it could be smooth wheel roller like this. In the field, we can compact with grid roller like this, depending on what type of soil we are using. We can compact, mostly clays are compacted with the sheep foot roller. It is not exactly sheep foot roller. It is a pad foot roller. Sheep foot roller is a little more projection, but they have projection for kneading action. Okay, and we can also have vibratory drum roller. So what we do is inside the smooth wood roller, we put weight on that. We let that weight move while it is rolling. That way, it hit the wall of the smooth wood roller, create vibration to cause vibration. Most of these type of rollers are used for granular soil like sand and gravel. And we also use pneumatic tire roller like that, where it is rolling with the pneumatic tire pressure. Okay, these are simply like a tires. And we also, if the area is small, we can also use vibratory plate rolling compaction, right? And we can also use power rammer. If you want to see power rammer, we have that in the lab. Okay, so this is smooth wheel roller, and this one is pad foot roller. Right, this smooth wheel, and this is pad foot roller, where you have projection little small compared to the sheep foot roller. And okay, so this is sheep foot roller. The projection is much more than the pad foot roller, but it's still smaller than the other one that I'll be showing you in a while. And then this is a rubber tire roller. So we roll the soil, we put weight on top of that, we roll it with the rubber tire pressure. Okay, so this is a smooth wheel roller, this is rubber tire roller, this is a grid roller, this is the tamping roller, and this is also tamper. But we talked about that. Okay, it's a vibratory plate, and this is the tamper that we use in the lab. Okay, so we also call them power rammers. Okay, with this we'll take another 5-minute break, and when we return back, you can take a 5-minute break and return back after 5 minutes, and we'll talk about what different moisture content that we need to consider to get the required hydraulic conductivity during compaction. It's extremely important. Okay. Okay, welcome back. So the compaction variables depend on different things. One variable is soil water content that we talked. Okay, so we talked about that. at optimum moisture content you have certain hydraulic conductivity. When you pass beyond the optimum moisture content and compact the soil, hydraulic conductivity reduces because the soil fabrics randomly oriented starts to orient parallel to each other. That way your vertical hydraulic conductivity reduces. Okay, but after certain amount of hydraulic conductivity, it gets to almost preferred orientation. That extra effort does not increase, does not change the orientation of the particle, so hydraulic conductivity does not increase. But if you increase the moisture content beyond that, dry unit weight decreases. That's not preferable. Okay. So influence of the molding water content, that is also moisture content of the soil at the time of molding or compaction, depends on hydraulic conductivity, as we saw there. So lower part of the diagram is the compaction curve, and the upper part is the change in hydraulic conductivity with that compaction effort. Right, the compaction curve shows you the dry unit weight versus moisture content effect, and then the optimum moisture content, as we talked, is the moisture content that gives you the peak or maximum dry unit weight. Then smallest hydraulic conductivity occurs when when the clay is molded slightly higher than the optimum moisture content. Typically the range is from 1 to 7% of the optimum moisture content, depending on the situation. Okay, depending on the type of soil. Okay, so it is important for the clay to be compacted when it is, in the field, we prefer the field moisture content or water content to be within the wet side of the optimum as opposed to the dry side of the optimum. Okay, example for that, you see the standard Proctor test optimum moisture content you get right at 12% moisture content. When we completed the standard Proctor test, took the soil out, it was like that. 16% in that soil, it is still, you could see the void space here that could increase the hydraulic conductivity of the hydraulic conductivity. When I increase the moisture, they increase the moisture content to 20%, now it is smooth and more preferred parallel orientation. So moisture content plays huge role in reducing the soil clots and at the same time the random orientation of the soil particles. Okay, if the soil is at the dry of optimum, then uncompacted soil contain dry and hard clods that are not easily broken during the compaction, like that, right? So that will create a huge pore. That will increase the hydraulic conductivity. Only way to get rid of that is you need to compact that with higher amount of energy. That way, that higher amount of energy is bringing the soil into closer to optimum moisture content situation for that particular energy. Okay, and that higher energy is good enough to break the clods. Okay, soil clods. Okay, if the excess water is permitted in the same soil, that if a lot of water you are using, then the pore pressures are developed in there, because then pore space is filled with a lot of water. So when we apply energy, that pore pressure will repel the energy back, and that will and that is not good. Okay, so while the mass is, when the soil is trying to shift from one location to the other, then the pore water pressure will block that. Will block that. It doesn't let the soil particle move. That will be against the increase in density of the soil. So less water is bad. A lot of water is bad too. For that reason, you need to have a zone between the optimum moisture content and the perfect zone where you get the optimum I would say optimum hydraulic conductivity. Okay, so the maximum dry density is mainly controlled by both the moisture content and the air void you have in the soil space that you already saw. So at the 0 air void situation, this is your line. Let's say if you consider 5% of the soil is filled with air void, that is, degree of saturation is 95%. So this particular soil, you get maximum dry density when the soil has the 95% degree of saturation. Right? When the soil has 90% degree of saturation, then the dry density is lower. So the situation is that moisture content caused the soil in the dry side of the optimum, which is not good. Okay, so gamma D is equal to, you see, GS gamma W, that over 1 plus WGS over degree of saturation, right, multiplied by degree of saturation. That'll give you the dry density of the, that way you can calculate the dry density of the soil when degree of saturation is not 100%. So this is GS gamma W over 1 plus E multiplied by degree of saturation. Okay, so in this particular case, if the dry unit, the specific gravity of the soil is 2.68, right, and we're talking about density, then dry density of the density of water is 1 gram per centimeter cube, okay, over 0.95, this is S, plus 0.12 moisture content, let's say, if the soil has 12% moisture content, multiplied by 2.68, right, multiplied by degree of saturation is 1 minus 0.95%, so 0.95, right, that will give me the 2 megagram per meter cube. So just correct this equation, okay. So gamma D is equal to GS gamma W over 1 plus E. So E, yes, E is equal to WGS. Okay, so GS gamma W over 1 plus WGS over S. So this S you have here is extra. Just simply get rid of that. So delete this S from your PowerPoint slide. Okay, this is a mistake. Okay, so 2.68 multiplied by 1 over this S goes to 1. So 0.95 plus 0.12 multiplied by 2.68 multiplied by whatever S you have in the denominator, that goes outside. So actually that is that denominator. So forget about this S, okay. So that will give me the dry unit weight of 2 megagram per meter cube. Okay, or 2 gram per centimeter cube. Okay, so the question was, can you get the dry density of the compacted soil? Oh, this was bad animation. Can you calculate the dry density of a compacted soil sample at the moisture content of 12% with degree of the air void of 5%, that means degree of saturation 95%, and specific gravity of soil is 2.68. So the equation is gamma D or rho D is GS gamma W or rho W. Rho D is equal to GS rho W over 1 plus E. Okay, so E is equal to WGS over S. Forget about this S. Okay, that way I calculated the dry the corresponding dry density would be 2 gram per centimeter cube or 2 megagram per meter cube. Okay, so the as we talked before, the hydraulic conductivity depends on the type of compaction as well. Okay, for example, we are talking for this particular soil, you see the optimum moisture content is about this is the optimum moisture content, right? So if you are compacting the soil at the dry side of the optimum moisture content, no matter whether you are using static compaction or kneading compaction, kneading is like the seafood roller. You apply pressure, so that way at the bottom and the top you get the same pressure. Okay, it's like kneading, and that way you have uniform pressure throughout, and it makes sure that it has uniform density throughout. Okay, so if it is the wet side of the optimum, then if you are, let's say, about 3 or 4% more than the wet side of the optimum, so it is 15, 17, 19, so 18% optimum. So if you do 5% more than the 4% more than the optimum, let's say 22% moisture content, the kneading gave you much lower hydraulic conductivity than the static compaction. You could see that. So the compaction effort depends on the type of compaction. The hydraulic conductivity corresponding to the compaction effort depends on the type of compaction. So static compaction, the soil is packed in a mold which is in a squeezed way with a piston to compress uniformly statically, right? So the void ratio at the top and bottom may be different, or at the center may be different. But in kneading, a probe or the pie-shaped metal piece that is attached to the drum, right, of the smooth wood roller is projected. That way, if you are pressurizing if this is a sheep foot, is the base of the drum, then you are getting pressure at the let's say 6 inch below, and you are also getting pressure 6 inch above or at the place on the surface. So you can get the same pressure at the surface and 6 foot below. 6 inches below. That way you get uniform pressure. Okay, so that way we push them. The metal plate will help. So the best type of field compaction equipment is always, drum roller with we call them shift foot roller. So drum roller with rods projected, as I told you, at the feet, and that they are sticking out from the drum, and then those rods penetrate into the soil, and they will destroy the clod. At the same time, they will also try to make uniform pressure throughout. Okay, so compaction, the hydraulic conductivity that you can get from the compaction also depends on the compaction effort, as we talked. For example, this is the, let's say, reduced compaction. This is the standard compaction, Proctor compaction. This is a modified Proctor compaction, you see. So if you do compaction, enormous amount of compaction effort, all of them for the same type of soil should merge into zero airport line, okay, where degree of saturation is 100%. Okay, so with increasing compaction effort, so you are getting maximum dry density in this soil, maximum unit weight dry density in soil at about 90% degree of saturation, right, is slightly more than 90%, and you are getting the maximum dry density here also at about 90%, here about 90%. That way you get maximum dry density at about 90% degree of saturation, right? But when you are increasing the compaction effort, so for example, if you are increasing if the compaction effort is less, then for the amount of moisture content, the hydraulic conductivity remains almost constant up to this point, right? Up to the, let's say this is less energy. So this is the dry side of the optimum. The optimum moisture content is about 20% here. So it is up to dry side of optimum, you get almost same hydraulic conductivity. All of a sudden, the hydraulic conductivity decreases. Still, the hydraulic conductivity was keeping on decreasing towards the wet side. So when we come to almost 100% saturation level, the hydraulic conductivity is much lower than the hydraulic conductivity that we are getting from the optimum moisture content. But now, with the increase in compaction effort here, your optimum moisture content is reduced to about 18%, right? So hydraulic conductivity is lower than the one that you got before. For the same moisture content, you see the huge difference here, much lower than what you got from the same effort, right? Okay, and still, if the amount of energy, moisture content increase, then although the dry density increases, hydraulic conductivity also decreases. Okay, hydraulic conductivity decreases, and it gives you, when it comes to the saturation level somewhere, then hydraulic conductivity is low. And now, if you increase the amount of energy further, then what happens is that extra amount of energy you are putting was useful to break the clots. Right? Now you have uniform reduction in hydraulic conductivity, and when it comes to optimum, the difference between the hydraulic conductivity that you are getting from the optimum to about 3 or 4% of the optimum is not a big difference. So higher energy is always good. But thing is, it's more expensive. So increased compaction effort results in the increased maximum soil density. That is obvious. We talked about that, and that will generally reduce the hydraulic conductivity. However, if the difference is strongly affected by moisture content, right? Basically, that difference is strongly affected by the difference, because you see here the difference is too high compared to the difference you are getting here, right? So at the higher moisture content or water content, the difference is not that big. You can see here, see all three efforts at higher moisture content, they give you almost same hydraulic conductivity, right? The two samples with same moisture content and similar density can have vastly different hydraulic conductivity when they were compacted with different energies. For example, same density, let's say this one 108, right? So this side you have much, let's say 108, right? And then the moisture content corresponding to give that 108 is about 15%. So here the hydraulic conductivity that you are getting from three different efforts are totally different. Okay, so always extra compaction energy may not make a huge density difference, but that will help to break the clots, that way reduce the void space and reduce the hydraulic conductivity. And we are more concerned with the hydraulic conductivity in compacted clay liner as opposed to density, strength, and those things. Okay, so if you can see another example here, you see modified Proctor test was done in same sample, and the standard Proctor test was done in the same sample, right? So if you see, let's say optimum moisture content with the standard Proctor was about 20%, okay, and then the hydraulic conductivity at the dry side of the standard Proctor is much higher than the weight, even up to the optimum moisture content point, right? So there's a huge variation from the dry side to the one approaching optimum moisture content, whereas the modified Proctor, you see there is a uniform reduction in hydraulic conductivity from certain percent less than the optimum to the optimum moisture content. So the modified Proctor test is somehow the lower optimum moisture content that we saw before in multiple examples, and the maximum dry density is always larger than that from the standard Proctor. We talked about that, and it is always advantageous to use the heavy compaction equipment. That way it gives you higher dry density, it gives you lower moisture content, and then lower than uniform reduction in hydraulic conductivity. Okay, so in landfill liners the higher energy is always good. Okay, so if you don't have equipment that gives you high energy, then you can increase the number of passes. That is something like that, like standard Proctor 3 layers, right? And modified you have 5 layers. So same thing in the field, you can increase the number of passes to increase the amount of energy you're putting into the soil. Okay, so the hydraulic conductivity is same example that I copied from there. So hydraulic conductivity, let's say at 12% moisture content, this is a 10%, 12% somewhere here, right? Hydraulic conductivity at 12% moisture content was about, you see here, about 10 to the power negative 4 here versus 10 to the power negative, I mean almost 10 to the power negative 11. So it is about 7 order of magnitude in log scale lower in the modified Proctor compaction effort, higher energy compared to the energy that we use for the standard Proctor compaction effort. Okay, so let's go to the 20% moisture content. At 20% moisture content, the density and the water content are almost same, because here you see no matter whether it is the modified also give you almost same density, standard also give you the same density, right? But the hydraulic conductivity from the modified is still about, let's say, 1 magnitude in log scale or slightly less than that, but it's still lower than the hydraulic conductivity that we got from the standard Proctor test. Okay, so it is always suggested that the standard Proctor test should be used in the lab to be more conservative, because in the lab you are using standard Proctor. That way in the lab you are getting lower higher hydraulic conductivity compared to the modified one. Okay, that way if you're getting higher, you tell that no, it is not in the field. Actually, if you're using higher compaction effort, you may end up getting lower hydraulic conductivity. That way you are in the conservative side. So always we want to have something larger number in the lab than in the field. That way you are in the conservative side. So applied compaction effort is generally expressed in terms of foot-pound per cubic foot, as I showed you in the diagram before. So for example, the Department of Navy specifies 4 to 6 passes of seafood roller with foot contact pressure of 250 to 500 pound per square inches for plasticity index more than 30, and 200 to 400 pound per square inches the compact pressure, the compaction pressure for the soil with plasticity index less than 30. Okay, the foot pressure is regulated so that the soil is not sheared in the 3rd or 4th passage. You see, so if you induce huge pressure into the soil, there is a possibility that you break the soil when you are rolling. So they are regulated. So this is the one way to specify how we control the compaction effort in the field. Here it is controlled by the pressure of the compaction device compaction equipment, sheep foot roller, pressure in the sheep foot roller, plus number of passes. Here you don't need to worry about the going to the field and measuring the dry unit weight and moisture content. But here you are checking how many number of passes were there. So there should be someone to note that. Okay, the contact pressure of the ship foot roller can always be adjusted by adjusting the amount of water inside, because the roller, you see, has a drum inside, right? And the drum, it can be, the amount of water you are putting in the drum will increase the amount of the weight you are pushing. Okay, that you can change. Both approaches, mostly the other approach is to calculate the number of passes based on laboratory compaction effort data. So the energy we are putting in the laboratory compaction to give me the hydraulic conductivity of 10 to the power 10 to negative 7 centimeter per second or lower, and then we just compare that with the energy that we are passing from one passes of the ship foot roller, let's say, whatever energy I'm getting, and then I divide that the total energy I'm putting in the lab to get that required hydraulic conductivity with the energy I'm putting for one pass to get the number of passes I need for the rolling. Okay, so now let's go to the compaction. The other thing that compaction effort that makes a difference in the hydraulic conductivity is the size of the clots that we talked before. Okay, so most lab proctor compaction tests, in the test what we do is first we open dry the sample, we cross them, we pulverize them to pass through number 4 sieve, and then we moisten that by adding certain moisture content as we talked before, and then with that moisture content we compact the soil. Okay, so if the clot size we have, let's say it is, the soil is passing through number 4 sieve, that is 0.2 inches sieve. So if you have big size particle in that, significant amount of big size particle there, let's say 0.2 inch clot, and at the same time you have let's say you take the soil that has huge amount of a small size particle, that's 0.75 inches particle. Okay, so large size particle, 0.75 inch particle is large size, so 0.2 inch in the lab. So in the lab, let's say the largest size particle you have is 0.2 inches. In the field you may have larger, let's say in the field you have 0.75 inch size particle. So that way you get a clot of the particle. So if you have small size, then when you add moisture content and compact that, then that you'll get uniform increase in density with the moisture content. So maximum dry density you're getting is somewhere here, right? It's about 107 or 8 pound per cubic foot, right? And when you have the soil sample in the field that has a larger clot size, more than 0.75 inches, close to 0.75 inches clot size, then with the same, by increasing amount of water and compacting that, you may end up getting same maximum dry density, but the optimum moisture content shifts significantly by 2 or 3%. Okay, so because optimum moisture content shifts significantly, because the clot size are bigger, hydraulic conductivity changes significantly as well. Okay, so here you can see there is a shift of 3% optimum moisture content for in the bigger size particle, bigger soil particle compared to the smaller soil particle. Okay, the 0.75 inch one need a little more water to reach into the optimum moisture content. Okay, so to get to the maximum dry density. For that reason, the condition of the compaction should be actually simulated as closely as possible to the lab, to make sure that the field situation is similar to the field situation in the lab. Okay, mostly in the field, if you get about 1 inch size per soil, sometimes we consider it's acceptable. So that means when we are doing into the when we are doing field lab compaction, we may want to put 1 inch maximum size as opposed to 0.2 inches using the standard. So always the maximum possible particle size, the soil size in the field should be similar to the maximum possible soil size in the lab. I mean opposite, right? Maximum possible particle size in the lab should be similar to the maximum expected soil size in the field. Okay, and one example is that, for example, you have different clot size, 0.2 inch clot size and 0.75 inch clot size. When they are molding at moisture content 12%, hydraulic conductivity was pretty low compared to 0.75 inches, right? And when they were molding with 16%, hydraulic conductivity of the smaller size particle reduced further, but the big size particle increased further, slightly increased. Okay, and then 18%, then hydraulic conductivity was reduced a little less than the previous case, but it's still reduced. But now, all of a sudden, that moisture content was good enough to break all those clots in the larger soil particle to drop the hydraulic conductivity to even a smaller number than the small clot, right? And then more moisture content helped more to reduce the hydraulic conductivity in the big clot, while when the moisture content was increased to 20% in the small clot, hydraulic conductivity doubled. So all those parametric studies should be done. Okay, so at the moisture content 12%, 16%, the larger size particle soil gave 4 to 6 order of magnitude higher the hydraulic conductivity, while at 18% and 20%, the larger size gave lower than the smaller one. Okay, so it's always important for us to make sure to figure out what will be the expected clot size in the field. Okay, for dry, hard soil. It is extremely important for the high plasticity, dry, hard soil compared to the low plasticity, soft soil. Because when we apply energy and water, we may break the clots. Okay, so it is always recommended to start compaction with smaller clots, like about 1 inches. Okay, so mostly in the field, the tillers and discs may be used for breaking them in the field, breaking the clays in the field, right? In the lab, we may use high-speed pulver mixture to break them. Okay, and we break them to reduce the clot size from the bigger size to the smaller, and then run the test in the lab. Okay, the other thing that we need to consider is the compaction effort. During compaction, we need to consider the bonding between the lifts. Okay, let's say you have 2 layers of soil you have here. One is a small projection, the other one is a big projection, right? So when you have a lift, then a smaller projection will need up to this point, and then below that we are not needing. But if the projection is pretty high, then what happens is when you are adding new layer, then all those soils were almost equally pressurized, right? When you add new layer, then you make sure that you see entire soil has almost same pressure. Here there is a gap between the properties between the base of the projection and the base of the previous compacted layer. Okay, so that's one important thing. The other thing is when we make a compaction, we do in lifts, typically 6 to 9 inch lift, right? And then we have to make sure that the compaction effort is uniform. So in the horizontal direction, when you have compaction up to this point, let's say we have compaction up to this point, and we're starting compaction from here, we need to scarify them, we need to make them rough. That way the bonding is pretty good between the horizontal joint. Same time for the vertical joint, right? And same time for the horizontal joint. You see, you finish one layer here, then you are adding one more layer. We have to make sure that we are scarifying them, we are making them rough. That way there is a good bond between the bottom layer and the layer above that. Okay, we have to be very careful. Otherwise, what happens is if there is a continuous crack or bond, the very weak bond, then there's a possibility the water move from here, go in this side, and come from here and quickly go to the ground, may quickly leak from the compacted clay liner. So we have to be very careful on that. So eliminating highly permeable zones between the lifts cut off the liquid flow from one lift to the other. Okay, and then that high permeability zone could be mainly because of poor compaction or could be because of poor bonding. So it's always useful to use the sheaf-footed rollers. They are the best kind to reduce the hydraulic connection between the defects. So sheaf-footed rollers are always good to have better bonding. And for example, the fully penetrating type sheaf-foot roller that has a shaft 9-inch tall shaft, it is longer than the thickness of the lift between the compaction. Typically compaction lift ranges from 6 to 9 inches, right? So that way that shaft can even penetrate to the layer below the previously compacted layer. Okay, mostly partially penetrating or in other words low projection foot rollers, we call them pad foot rollers. They cannot, like for example, they cannot penetrate to the old layer, right? So that may create the zone of heterogeneous permeability. It's not good. Okay, so another way to blend the lift is by making scarifying the layers roughly. That way they have very good bonding between previously laid and compacted and the freshly compacted layer. So we talked about that. So commonly in the construction of the soil liner, the finished lift is sealed with a smooth steel drum roller to minimize the desiccation erosion. So what we do is, after we are compacting, we put a layer of soil and we seal them, right? That will control erosion, plus that will control desiccation, evaporation and desiccation cracking. Okay, so the soil must be broken up with a disc before a new lift is placed on it, because you may end up having desiccation cracking there. Okay, so sometimes people use plastic to cover them. That way to reduce the desiccation cracking. But before we put the new one, it's always good to break them first and then put the new layer. Okay, the other thing that we need to think is, sometimes, for below ground disposal pits, right? There are two different pits. So even in Southern California, you can see two different types of pit. One is above the ground. You are dumping the soil above the ground. So, but most of the time we go below the ground pits. Okay, so we make excavation and put our clay liner much below the horizontal ground level. Okay, so it may need to construct a liner. These are liners, you see, you may end up constructing these liners, and mostly, yes, you need to do that in a slope, right? So mostly, depending on the situation, sometimes we replace them with a compacted geosynthetic clay liner or the composite liners, but most of the time we need compacted clay liners even in the side slopes. Okay, we do those compaction two ways. One way is to make the inclined layer of compaction. The other way is to make the horizontal layer of compaction. Okay, so in the horizontal lift, we have to make sure that at least we are putting 12 foot wide. That way we have compaction equipment are passing from one place to the other, right? In the parallel safety, we cannot make the slope more than 2.5 horizontal to 1 vertical, because if you make it steeper, then you have slope stability problems. Soil may fall from there. You may not be able to even retain the soil on place, retain the previously compacted layer on place. Okay, so as we talked about the desiccation cracking, so desiccation cracking will create huge highly permeable zone. We have to reduce that. There are different ways to reduce that. So a dry environment or freezing of the liner can cause the liner to lose moisture, right? So freezing lose moisture because the water converts into ice. The drying lose moisture because it evaporates the water out. So the potential of soil liner desiccation increases if the capillary break exists between the liner. Okay, so that capillary break means there is no continuous move of the capillary water. So if you have capillary water coming up, then that will moisten the soil, reduce the desiccation cracking. But if there is a break between the capillary water, then the soil keeps on drying with the increase in temperature, and that will cause desiccation cracking. Okay, so that we have to be very careful on that. So when the compacted clay liner freezes, then hydraulic conductivity increases after the liner thaws. We talked about that before. Okay, so during the construction, moisture can be maintained by different ways. One is by proof rolling, as we talked. We just simply put the soil and roll them using the rubber tire roller or a smooth wheel roller or something, because you don't want to scarify them. Just simply smooth wheel roller, roll them. That way you are putting a layer of the soil that is protecting the lower layer of the soil that we compacted, right? And then next day when we come, we simply scarify that soil or powder that soil or pulverize that soil in different ways and recompact them. And the other way is to cover that with the geomembrane or plastic sheets. Okay, so compaction equipment also plays an important role in the hydraulic conductivity of the compacted clay liner. Okay, for example, heavy rollers, they are over 50 kips capacity, and has a long penetrating feet that will give the pressure of about 3 to 5 kips per foot along the drum surface, at the drum surface, because they are projected. So at the drum surface, the pressure is about 3 to 5 kips per linear foot. Okay, but medium weight roller ranges from about 30 kips to 50 kip. The weight, that the capacity. Light weight rollers are 15 to 30 kips capacity. That'll give only about you see, half kips per foot of pressure. Because they are giving less pressure, definitely the bonding is different, void ratio is different, compaction the density will be different. So for that reason, we have to make sure that which roller will be used in the field, and then how many number of passes we have to apply for that. So variable, for example, if you have vibrator rollers that we use for the compaction of sand and gravel, so they are about 20 to 30 kips static weight capacity. They are not effective for the clay compaction. Okay, but smooth wheel rollers, the shift foot rollers are the best. But it's always, they have a special piece of vibration equipment inside the drum, right, that works perfectly for granular soil, because granular soils are compacted well by vibration. But it's not good for the clay. Shift foot roller is the best for the clay, because they provide same pressure everywhere. Okay, so the reason vibrator rollers are not good is mainly because the projection is very short, right, and because they have short projection, then the kneading action is not effective. That way you have a separation between two layers, and they have heterogeneous hydraulic conductivity, right? And then the other reason for that is the half of its static weight goes to the rear axle and the rubber tire, and not to the roller itself. Okay, shift foot rollers are better because they have a longer projection, and I talked about that 3 or 4 times, right? And they have same pressure at top and bottom. At the same time, they have high compaction stress at the tip, right? That ranges from 200 to 700 pounds per square inches. And then inside the drum, you can fill the drum with water to increase the pressure that we talked about. So mostly in the field, when you drive, you see a lot of smooth wheel roller as opposed to the shift foot roller, because smooth wheel rollers are good for different purposes, so people produce more on that. So they produce very few of shift foot roller. They are good for liners, but may not be good for other type of soil or compaction. The compaction in highways or something like that. Okay, so sometimes the size of the landfill will become a limitation for the heavy large compactors, because if your landfill cell is small, or if the access road is a problem, then we may end up going with smaller one. Okay, so the recommended design procedure is this. That recommended design procedure comes with different factors. That comes with the shear strength, that comes with the permeability of the soil, that comes with the other parameters like desiccation, cracking, all those things, right? So one example is, let's say we say, okay, in the field, to get the hydraulic conductivity lower than 10 to -7 centimeter per second for that particular soil, with the standard compaction effort, the moisture content should be between +1 to +5% of the optimum moisture content. So if that moisture content gave me hydraulic conductivity less than 10 to -7 centimeter per second, then the density I needed is more than, let's say, 90% of the maximum dry density, then I can make a zone of compliance like that tells, okay, this is the acceptable zone. We talked about that in the past. Okay, so the traditional method for the specification, to write the specification of the acceptable water content and dry unit weight of the compacted clay liners are decided based on different factors. In the past, that was mainly because of 90% relative compaction and the moisture content ranging from optimum to 4% of the optimum.
Now it is changing a little bit because we look into more factors. For example, you see, if you see the compaction curve, right? Modified compaction curve you have is the broken line you have here that tells you what is the related dry unit weight corresponding to different molding moisture content, right? And if you see the hydraulic conductivity of the soil, right, at different density and the moisture content, right, you can do that test in the lab in different ways. For the relationship between density moisture content, if you make a contour of dry unit weight versus molding moisture content, you measure the moisture content for hydraulic conductivity of the soil, compact it with different moisture content, give you different dry unit weight, then you can make contour. So this combination of dry unit weight and moisture content gives you hydraulic conductivity less than 10 to negative 5 centimeter per second, which is not acceptable, right? So 10 to negative 6, which is not acceptable. Only thing that you can accept is hydraulic conductivity less than 10 to negative 7 centimeter per second. Right? So if you plot the previous figure that you see, our specification tells that, okay, the maximum dry density, the dry density in the field should be more than, let's say, 90% of the maximum dry density you are getting, and the moisture content should be in between optimum moisture content to optimum moisture content plus 4. So that is, let's say, 14% to 18%. Right? So in reality, if we are with a traditional, very traditional way of specifying the material in the field, then you go with 90% additive compaction and optimum plus or minus 4%. Right? So this will be your zone of compliance. So see here, even though this is in the zone of compliance, you see, for example, if you are talking about this point here, okay, which has, let's say, density of the soil is about 108 pound per cubic foot, and the moisture content of that soil is about 17%. Then, even though from the traditional way of specifying it, it was acceptable, but if you see the hydraulic conductivity of that soil, it is 10 to negative 5 centimeter per second, which is not acceptable. Right? For that reason, it's always look into all angles. Okay, so contours of the constant hydraulic conductivity for a silty clay compacted with kneading compaction is shown here. I mean, these are contours, right? So it is also shown in the modified Proctor compaction. So from our traditional way, it was fine, acceptable. For in reality, if you check the hydraulic conductivity, this compaction effort may not be sufficient to give you hydraulic conductivity higher than 10 to and lower than 10 to negative 7. So what I do is now I would limit that compliance zone that we talked before, that based on the relative density and the moisture content only, and what we do is 10 to the power, the contour of 10 to negative 7 centimeter per second. So anything we have here, then the hatch line, we continue the hatch line above that line, but we completely wipe the hatch line below that. Now I have another zone of compliance here. Okay, so we keep on doing that. So different compaction efforts you have, right? And then depending on the compaction effort, traditionally you have a maximum dry density, and then for example, let's see the less compaction effort you have here. So maximum dry density, you are getting this, and 90% of that will give dry density here. So there is zone of compliance, right? And then you get the moisture content from optimum moisture content to 4% of the optimum moisture content. That way you get the zone of compliance with different compaction efforts, right? But what we do is we cut off everything here from the hydraulic conductivity also. That way we get a zone here that gives me, for different compaction efforts, that gives me hydraulic conductivity less than 10 to negative 7 centimeter per second. So this is nothing, but this is continuation of this figure. You see, what we do is we cut off everything from 10 to the power negative 7 centimeter per second hydraulic conductivity. Okay, so even we can cut that further with different other criteria. For example, if I don't want to have the molding moisture content less than certain moisture content, because here you see, if you don't tell moisture content ranging from this percent to this percent, then it will be in trouble. For that reason, what we do now is, now we say, okay, the moisture content ranging from this moisture content to this moisture content. and the dry density ranging from a certain percentage of the maximum dry density for that compaction effort. Okay, so like that. So we have different, and then third thing we have to consider now, the other thing that we came up with all this chart here, right? Now the other thing that we have to consider is based on the shear strength. Sometimes, if the landfill site gives you huge pressure on the compacted clay liner, there's a possibility that your liner will fail in bearing capacity failure. And there, the shear strength should also be something, right? So what we do is minimum shear strength of the soil that you are getting. So we make the relationship between moisture content, dry unit weight, and the shear strength. Unconfined, mostly we check unconfined compressive strength of that soil. And then anything combination that gives me unconfined compressive strength higher than required, then I just hash them, right? So dry will always give you higher unconfined compressive strength, but may not be good for permeability point of view. Okay, so then now this area is now limited. This area is now limited within that dark zone from the strength point of view. Okay, this cannot give you high strength because water is too much. Okay, now if you want to add more, from now you got the strength point of view, right? And you may want to add one more thing based on, you see, this line is based on the hydraulic conductivity. Now we have based on the strength, right? Now if you think about the shrinkage and swelling behavior, so if you need to cut it down to less moisture content because you have a lot of water, then the shrinkage swelling behavior will be pretty high. Right now, because of shrinkage and swelling behavior, now your zone is now further reduced to this small. So that way you have to put all efforts to get the acceptable condition, and that will give you the zone of compliance. Now your zone of compliance is from this dry unit weight to this dry unit weight in this zone, right? So now before, in the previous case, you had a huge zone of compliance. Now it is reduced significantly to a small zone of compliance. Okay, this is the way how we control the zone of compliance in the field. So this is zone of compliance based on the hydraulic conductivity. This is the zone of compliance based on the strength. This is the zone of compliance based on the shrinkage, right? And then if you combine all of them, this tiny space is the actual overall zone of compliance. Okay, so use of hydraulic conductivity, shear strength, and the shrinkage data to define a single acceptable zone is quite common lately. That is called the overall zone of compliance, and you can get that from the lab test. If you do parametric study in the lab test with different compaction efforts, then you can easily make them. Okay, so this completes the compacted clay liner, and we'll come up with totally new topic next week. Until then, have a great weekend. I'll see you next week.